Dancing Wu Li Masters by Gary Zukav. Abridged, read by Vincent Bagnall. Introduction. My first exposure to quantum physics occurred a few years ago when a friend invited me to an afternoon conference at the Lawrence Berkeley Laboratory in Berkeley, California. At that time, I had no connections with the scientific community, so I went to see what physicists were like. To my great surprise, I discovered that I understood everything that they said, and their discussions sounded very much like a theological discussion. I scarcely could believe what I had discovered. Physics was not the sterile, boring discipline that I had assumed it to be. It was a rich, profound venture which had become inseparable from philosophy. Incredibly, no one but physicists seemed to be aware of this remarkable development. As my interest in and knowledge of physics grew, I resolved to share this discovery with others. This book is a gift of my discovery. It is one of a series. Generally speaking, people can be grouped into two categories of intellectual preference. The first group prefers explorations which require a precision of logical processes. These are the people who become interested in the natural sciences and mathematics. They do not become scientists because of their education. They choose a scientific education because it gratifies their scientific mental set. The second group prefers explorations which involve the intellect in a less logically rigorous manner. These are the people who become interested in the liberal arts. They do not have a liberal arts mentality because of their education. They choose a liberal arts education because it gratifies their liberal arts mental set. And since both groups are intelligent, it is not difficult for members of one group to understand what members of the other group are studying. However, I've discovered a notable communication problem between the two groups. Many times my physicist friends have attempted to explain a concept to me and, in their exasperation, have tried one explanation after another, each one of which sounded abstract and generally abstruse. When I could comprehend, at last, what they were trying to communicate, inevitably I was surprised to discover that the idea itself was actually quite simple. Conversely, I often have tried to explain a concept in terms which seemed to me laudably lucid, but which to my exasperation seemed hopelessly vague, ambiguous, and lacking in precision to my physicist friends. I hope that this book will be a useful translation which will help those people who do not have a scientific mental set, like me, to understand the extraordinary process which is occurring in theoretical physics. Like any translation, it is not as good as the original work, and of course it is subject to the shortcomings of the translator. For better or worse, my first qualification as a translator is that, like you, I am not a physicist. To compensate for my lack of education in physics and for my liberal arts mentality, I asked and received the assistance of an extraordinary group of physicists. As each chapter was completed, I sent a copy of it to each physicist and asked him to correct any conceptual or factual errors which he found. Several other physicists read selected chapters. My original intention was to use these comments to correct the text. However, I soon discovered that my physicist friends had given more attention to the manuscript than I had dared to hope. Not only were their comments thoughtful and penetrating, but taken together, they formed a significant volume of information by themselves. The more I studied them, the more strongly I felt that I should share these comments with you. Therefore, in addition to correcting the manuscript with them, I also included in the footnotes those comments which do not duplicate the corrected text. The new physics, as it is used in this book, means quantum mechanics, which began with Max Planck's theory of quanta in 1900, and relativity, which began with Albert Einstein's special theory of relativity in 1905. The old physics is the physics of Isaac Newton, which he discovered about 300 years ago. Classical physics means any physics that attempts to explain reality in such a manner that for every element of physical reality, there is a corresponding element in the theory. Therefore, classical physics includes the physics of Isaac Newton and relativity, both of which are structured in this one-to-one manner. It does not, however, include quantum mechanics, which, as we shall see, is one of the things that makes quantum mechanics unique. Be gentle with yourself as you read. This book contains many rich and multifaceted stories, all of which are heady stuff. Pun. You cannot learn them all at once, any more than you can learn the stories told in War and Peace, Crime and Punishment, and Les Miserables all at once. I suggest that you read this book for your pleasure, and not to learn what is in it. By enjoying yourself, you probably will remember more than if you had set about to learn it all. One last note. This is not a book about physics and Eastern philosophies. Although the poetic framework of Wu Li is conducive to such comparisons, this book is about quantum physics and relativity. In the future, I hope to write another book specifically about physics and Buddhism. In view of the Eastern flavor of Wu Li, however, I have included in this book those similarities between Eastern philosophies and physics that seemed to me so obvious and significant that I felt I would be doing you a disservice if I did not mention them in passing. Happy reading. Gary Zukav. San Francisco, July 1978. Part 1. Wu Li? Big week at Big Sur. When I tell my friends that I study physics, they move their heads from side to side. They shake their hands at the wrist, and they whistle, "Whew, that's difficult." Now, this universal reaction to the word physics is a wall that stands between what physicists do and what most people think they do. There's usually a big difference between the two. Physicists themselves are partly to blame for this sad situation. Their shop talk sounds like advanced Greek, unless you are Greek or a physicist. When they're not talking to other physicists speak English. Ask them what they do, however, and they sound like the natives of Corfu again. On the other hand, part of the blame is ours. Generally speaking, we have given up trying to understand what physicists and biologists, etc., really do. In this, we do ourselves a disservice. These people are engaged in extremely interesting adventures that are not that difficult to understand. True, how they do what they do sometimes entails a technical explanation, which, if you are not an expert, can produce an involuntary deep sleep. What physicists do, however, is actually quite simple. They wonder what the universe is really made of, how it works, what we are doing in it, and where it is going, if it is going any place at all. In short, they do the same things that we do on starry nights when we look up at the vastness of the universe and feel overwhelmed by it and a part of it at the same time. That is what physicists really do, and the clever rascals get paid for doing it. Unfortunately, when most people think of physics, they think of chalkboards covered with undecipherable symbols of an unknown mathematics. The fact is that physics is not mathematics. Physics, in essence, is simple wonder at the way things are and a divine, some call it compulsive, interest in how that is so. Mathematics is the tool of physics. Stripped of mathematics, physics becomes pure enchantment. I had spoken often to a friend who was a physicist about the possibility of writing a book, unencumbered with technicalities and mathematics, to explain the exciting insights that motivate current physics. So, when he invited me to a conference on physics that he and Michael Murphy were arranging at the Esalen Institute, the Esalen Institute, it is named for an Indian tribe, is in Northern California. The Northern California coast is an awesome combination of power and beauty, but nowhere so much as along the Pacific Coast Highway, between the towns of Big Sur and San Luis Obispo. The Esalen facilities are located about a half hour south of Big Sur between the highway and the coastal mountains on the one side and rugged cliffs overlooking the Pacific Ocean on the other. A dancing stream divides the northern third of the grounds from the remainder. On that side is a big house called the Big House, where guests stay and groups meet, along with a small home where Dick Price, co-founder of Esalen with Murphy, stays with his family. On the other side of the stream is a lodge, where meals are served and meetings are held, accommodations for guests and staff, and hot sulfur baths. Dinner is a multi-dimensional experience. I joined the two men who already were eating. One was David Finkelstein, a physicist from Yeshiva University in New York, who was attending the conference on physics. The other was Al Chung-Liang Huang, a Tai Chi master. I could not have chosen better companions. The conversation soon turned to physics. When I studied physics in Taiwan, said Huang, we called it Wu Li, pronounced Wu Li. It means patterns of organic energy. Everyone at the table was taken at once by this image. Mental lights flashed on, one by one, as the idea penetrated. Wu Li was more than poetic. It was the best definition of physics that the conference would produce. It caught that certain something, that living quality that we were seeking to express in a book, that thing without which physics becomes sterile. Let's write a book about Wu Li, I heard myself exclaim. Immediately ideas and energy began to flow, and in one stroke, all of the prior planning that I had done went out the window. From that pooling of energy came the image of dancing Wu Li masters. My remaining days at Esalen, and those that followed, were devoted to finding out what Wu Li masters are and why they dance. All of us sensed with excitement and certitude that we had discovered the channel through which the very things that we wanted to say about physics would flow. The Chinese language does not use an alphabet like Western languages. Each word in Chinese is depicted by a character, which is a line drawing. Sometimes two or more characters are combined to form different meanings. This is why it is difficult to translate Chinese into English. Good translations require a translator who is both a poet and a linguist. For example, Wu can mean either matter or energy. Li is a richly poetic word. It means universal order or universal law. It also means organic patterns. The grain in a panel of wood is Li. The organic pattern on the surface of a leaf is also Li, and so is the texture of a rose petal. In short, Wu Li, the Chinese word for physics, means patterns of organic energy, matter, energy, Wu, plus universal order organic patterns, Li. This is remarkable, since it reflects a worldview which the founders of Western science, Galileo and Newton, simply did not comprehend, but toward which virtually every physical theory of import in the 20th century is pointing. The question is not, do they know something that we don't? The question is, how do they know it? English words can be pronounced almost any way, without changing their meanings. I was 5 years a college graduate before I learned to pronounce consummate as an adjective, consummate. It means carried to the utmost extent or degree, perfect. I live in anguish when I think of the times that I have spoken of consummate linguists, consummate scholars, etc. Someone always seemed to be holding back a smile almost. I learned later that these were the people who read dictionaries. Nonetheless, my bad pronunciation never prevented me from being understood. That is because inflections do not change the denotation of an English word. No, spoken with a rising inflection, no, with a downward inflection, no, and with no inflection, no, all mean, according to the dictionary, a denial, a refusal, negative. This is not so in Chinese. Most Chinese syllables can be pronounced several different ways. Each different pronunciation is a different word, which is written differently and which has a meaning of its own. Therefore, the same syllable pronounced with different inflections, which unaccustomed Western listeners scarcely can distinguish, constitutes distinctly separate words, each with its own ideogram and meaning to a Chinese listener. In English, which is an atonal language, these different ideograms are all written and pronounced the same way. For example, there are over 80 different wus in Chinese, all of which are spelled and pronounced the same way in English. Al Huang has taken 5 of these wus, each of which when combined with li produces a different Wu Li, each with the same English spelling, and each pronounced in English Wu Li. The first Wu Li means patterns of organic energy. This is the Chinese way of saying physics. Wu means matter or energy. The second Wu Li means my way. Wu means mine or self. The third Wu Li means nonsense. Wu means void or non-being. The fourth Wu Li means I clutch my ideas. Wu means to make a fist or clutch with a closed hand. The fifth Wu Li means enlightenment. Wu means enlightenment or my heart, my mind. If we were to stand behind a master weaver as he begins to work his loom, we would see at first not cloth, but a multitude of brightly colored threads from which he picks and chooses with his expert eye and feeds into the moving shuttle. As we continue to watch, the threads blend one into the other. A fabric appears, and on the fabric, behold, a pattern emerges. In a similar manner, Al Huang has created a beautiful tapestry from his own epistemological loom. Physics equals Wu Li. Wu Li equals patterns of organic energy. Wu Li equals my way. Wu Li equals nonsense. Wu Li equals I clutch my ideas. Wu Li equals enlightenment. Each of the physicists at the conference, to a person, reported a resonance with this rich metaphor. Here at last was the vehicle through which we could present the seminal elements of advanced physics. By the end of the week, everyone at Esalen was talking about Wu Li. At the same time that this was happening, I was trying to find out what a master is. The dictionary was no help. All of its definitions involved an element of control, and this did not fit easily into our image of the dancing Wu Li masters. Since Al Huang is a Tai Chi master, I asked him, "That is the word that other people use to describe me," he said. To Al Huang was just Al Huang. Later in the week, I asked him the same question again, hoping to get a more tangible answer. A master is someone who started before you did, was what I got that time. My Western education left me unable to accept a non-definition for my definition of a master. So I began to read Huang's book, Embrace Tiger, Return to Mountain. There, in the foreword by Alan Watts, in a paragraph describing Al Huang, I found what I sought. Said Alan Watts of Al Huang, "He begins from the center and not from the fringe. He imparts an understanding of the basic principles of the art before going on to the meticulous details. And he refuses to break down the Tai Chi movements into a 1-2-3 drill so as to make the student into a robot. The traditional way is to teach by rote and to give the impression that long periods of boredom are the most essential part of training. In that way, a student may go on for years and years without ever getting the feel of what he is doing." Here was just the definition of a master that I sought. A master teaches essence. When the essence is perceived, he teaches what is necessary to expand the perception. The Wu Li master does not speak of gravity until the student stands in wonder at the flower petal falling to the ground. He does not speak of laws until the student of his own says, "How strange." I dropped 2 stones simultaneously, one heavy and one light, and both of them reached the earth at the same moment. He does not speak of mathematics until the student says, "There must be a way to express this more simply." In this way, the Wu Li master dances with his student. The Wu Li master does not teach, but the student learns. The Wu Li master always begins at the center, at the heart of the matter. And this is the approach that we take in this book. It is written for intelligent people who want to know about advanced physics, but who are ignorant of its terminology and perhaps of its mathematics. The Dancing Wu Li Masters is a book of essence, the essence of quantum mechanics, quantum logic, special relativity, general relativity, and some new ideas that indicate the direction that physics seems to be moving. Of course, who can know where the future goes? The only surety is that what we think today will be a part of the past tomorrow. Therefore, this book deals not with knowledge, which is always past tense anyway, but with imagination, which is physics come alive, which is Wu Li. One of the greatest physicists of all, Albert Einstein, was perhaps a Wu Li master. In 1938, he wrote, "Physical concepts are free creations of the human mind, and are not, however it may seem, uniquely determined by the external world. In our endeavor to understand reality, we are somewhat like a man trying to understand the mechanism of a closed watch. He sees the face and the moving hands, even hears its ticking, but he has no way of opening the case. If he is ingenious, he may form some picture of a mechanism which could be responsible for all the things he observes, but he may never be quite sure his picture is the only one which could explain his observations. He will never be able to compare his picture with the real mechanism, and he cannot even imagine the possibility of the meaning of such a comparison." Most people believe that physicists are explaining the world. Some physicists even believe that. But the Wu Li masters know that they are only dancing with it. I asked Huang how he structures his classes. "Every lesson is the first lesson," he told me. "Every time we dance, we do it for the first time." "But surely you cannot be starting new each lesson," I said. "Lesson number 2 must be built on what you taught in lesson number 1, and lesson 3 likewise must be built on lessons 1 and 2, and so on." "When I say that every lesson is the first lesson," he replied, "it does not mean that we forget what we already know. It means that what we are doing is always new, because we are always doing it for the first time." This is another characteristic of a master. Whatever he does with the enthusiasm of doing it for the first time. And this is the source of his unlimited energy. Every lesson that he teaches or learns is a first lesson. Every dance that he dances for the first time. It is always new, personal, and alive. Nobel Prize winner in physics and the former chairman of the physics department at Columbia University wrote, "We don't teach our students enough of the intellectual content of experiments, their novelty and their capacity for opening new fields. My own view is that you take these things personally. You do an experiment because your own philosophy makes you want to know the result. It's too hard, and life is too short to spend your time doing something because someone else has said it's important. You must feel the thing yourself." Unfortunately, most physicists are not like Rabi. The majority of them, in fact, do spend their lives doing what other people have told them is important. And that was the point Rabi was making. This brings us to a common misunderstanding. When most people say scientist, they mean technician. A technician is a highly trained person whose job is to apply known techniques and principles. He deals with the known. A scientist is a person who seeks to know the true nature of physical reality. He deals with the unknown. In short, scientists discover and technicians apply. However, it is no longer evident whether scientists really discover new things or whether they create them. Many people believe that discovery is actually an act of creation. If this is so, then the distinction between scientists, poets, painters, and writers is not clear. In fact, it is possible that scientists, poets, painters, and writers are all members of the same family of people whose gift it is, by nature, to take those things which we call commonplace and to represent them to us in such ways that our self-imposed limitations are expanded. Those people in whom this gift is essentially pronounced, we call geniuses. The fact is that most scientists are technicians. They are not interested in the essentially new. Their field of vision is relatively narrow. Their energies are directed toward applying what is already known. Because their noses often are buried in the bark of a particular tree, it is difficult to speak meaningfully to them of forests. The case of the mysterious hydrogen spectrum illustrates the difference between scientists and technicians. When a white light, such as sunlight, enters a glass prism, one of the most beautiful of phenomena occurs. Out the other side of the prism comes not white light, but every color in the rainbow, from dark red to light violet, with orange, yellow, green, and blue in between. And this is because white light is made of all these different colors. It is a combination, whereas red light contains only red light. green light contains only green light, etc. Isaac Newton wrote his famous Optics about this phenomenon 300 years ago. This display of colors is called a white light spectrum. The spectral analysis of white light shows a complete spectrum because white light contains all of the colors that our eyes can see, and some that they cannot see, like infrared and ultraviolet. However, not every spectral analysis produces a complete spectrum. If we take one of the chemical elements, for example, like sodium, cause it to emit light and shine that light through a glass prism, we get only part of a complete spectrum. If an object is visible in a dark room, it is emitting light. If it appears red, for example, it is emitting red light. Light is emitted by excited objects. Exciting a piece of sodium does not mean offering it tickets to the Super Bowl. Exciting a piece of sodium means adding some energy to it. One way of doing this is to heat it. When we shine the light emitted by excited incandescent sodium through a prism or spectroscope, we do not obtain the full array of colors characteristic of white light, but only parts of it. In the case of sodium, we obtain two thin yellow lines. We also can produce a negative image of the sodium spectrum by shining white light through sodium vapor to see what parts of the white light the sodium vapor absorbs. White light passing through sodium vapor and then through a spectroscope produces the whole rainbow of colors minus the two yellow lines emitted by incandescent sodium. Either way, the sodium spectrum always produces the same distinct pattern. It may be composed of black lines on an otherwise complete spectrum of colors, or it may be composed of colored lines without the rest of the spectrum, but it always remains the same. This pattern is the fingerprint of the element sodium. Each element emits or absorbs only specific colors. Likewise, each element produces a specific spectroscopic pattern which never varies. Hydrogen is the simplest element. It seems to have only two components, a proton, which has a positive charge, and an electron, which has a negative charge. We must say it seems to have because there is not one person alive who has ever seen a hydrogen atom. If hydrogen atoms exist, millions of them can exist on a pinhead. So small are they calculated to be. Hydrogen atoms is a speculation about what is inside of the watch. We can say only that the existence of such entities nicely explains certain observations that would be very different to explain otherwise, barring explanations such as the devil did it, which still may prove to be correct. It is this kind of explanation that drove Galileo, Newton, and Descartes to create what is now modern science. At one time, physicists thought that atoms were constructed in the following way. At the center of an atom is a nucleus, just as the sun is the center of our solar system. In the nucleus is located almost all of the mass of the atom in the form of positively charged particles or protons, and particles about the same size as protons, but without a charge, neutrons. Only hydrogen has no neutrons in its nucleus. Orbiting about the nucleus, as the planets orbit the sun, are electrons, which have almost no mass compared with the nucleus. Each electron has one negative charge. The number of electrons is always the same as the number of protons, so that the positive and negative charges cancel each other, and the atom as a whole has no charge. This is a book about physics, therefore all it contains is a description. It cannot contain the experience itself. This does not mean that you will not have the experience of physics by reading it. It only means that if you do, the experience is coming from you and not from the book. Quantum mechanics, for example, shows us that we are not as separate from the rest of the world as we once thought. Particle physics shows us that the rest of the world does not sit idly out there. It is a sparkling realm of continual creation, transformation, and annihilation. The ideas of the new physics, when wholly grasped, can produce extraordinary experiences. The study of relativity theory, for example. can produce the remarkable experience that space and time are only mental constructions. Each of these different experiences is capable of changing us in such ways that we never again are able to view the world as we did before. There is no single experience of physics. The experience always is changing. Relativity and quantum mechanics, although generally unknown to non-physicists, are more than a half-century old. Today, the entire field of physics is quivering with anticipation. The air is charged with excitement. A feeling is shared among physicists that radical change is at hand. A consensus grows that the near future will see new theories exploding onto the scene, incorporating the older theories and giving us a much larger view of our universe and, consequently, of ourselves. The Wu Li masters move in the midst of all this, now dancing this way, now that, sometimes with a heavy beat, sometimes with a lightness and grace, ever flowing freely. Now they become the dance, now the dance becomes them. This is the message of the Wu Li masters, not to confuse the type of dance that they are doing with the fact that they are dancing. 1. Einstein doesn't like it. Quantum mechanics are not the fellows who repair automobiles in Mr. Quantum's garage. Quantum mechanics is a branch of physics. There are several branches of physics. Most physicists believe that sooner or later they will construct an overview large enough to incorporate them all. According to this point of view, we eventually will develop in principle a theory which is capable of explaining everything so well that there will be nothing left to explain. This does not mean, of course, that our explanation necessarily will reflect the way that things actually are. We still will not be able to open the watch, as Einstein put it, but every occurrence in the real world, inside the watch, will be accounted for by a corresponding element of our final super theory. We will have, at last, a theory that is consistent within itself and which explains all observable phenomena. Einstein called this state the ideal limit of knowledge. This way of thinking runs into quantum mechanics the same way that the car runs into the proverbial brick wall. Einstein spent a large portion of his career arguing against quantum mechanics, even though he himself made major contributions to its development. Why did he do this? To ask this question is to stand at the edge of an abyss, still on the solid ground of Newtonian physics, but looking into the void. To answer it is to leap boldly into the new physics. Quantum mechanics forced itself upon the scene at the beginning of this century. No convention of physicists voted to start a new branch of physics called quantum mechanics. No one had any choice in the matter, except perhaps what to call it. A quantum is a quantity of something, a specific amount. Mechanics is the study of motion. Therefore, quantum mechanics is the study of the motion of quantities. Quantum theory says that nature comes in bits and pieces, quanta, and quantum mechanics is the study of this phenomenon. Quantum mechanics does not replace Newtonian physics, it includes it. The physics of Newton remains valid within its limits. To say that we have made a major new discovery about nature is one side of a coin. The other side of the coin is to say that we have found the limits of our previous theories. What we actually discover is that the way that we have been looking at nature is no longer comprehensive enough to explain all that we can observe, and we are forced to develop a more inclusive view. In Einstein's words, creating a new theory is not like destroying an old barn and erecting a skyscraper in its place. It is rather like climbing a mountain, gaining new and wider views, discovering unexpected connections between our starting point and its rich environment. But the point from which we started out still exists and can be seen, although it appears smaller and forms a tiny part of our broad view, gained by the mastery of the obstacles in our adventurous way up. Newtonian physics still is applicable to the large-scale world, but it does not work in the subatomic realm. Quantum mechanics resulted from the study of the subatomic realm. that invisible universe underlying, embedded in, and forming the fabric of everything around us. In Newton's age, late 1600s, this realm was entirely speculation. The idea that the atom is the invisible building block of nature was proposed about 400 years before Christ, but until the late 1800s, it remained just an idea. Then physicists developed the technology to observe the effects of atomic phenomena, thereby proving that atoms exist. Of course, what they really proved was that the theoretical existence of atoms was the best explanation of the experimental data that anyone could invent at the time. They also proved that atoms are not indivisible, but themselves are made of particles smaller yet, such as electrons, protons, and neutrons. These new particles were labeled elementary particles because physicists believed that at last they really had discovered the ultimate building blocks of the universe. The elementary particle theory is a recent version of an old Greek idea. To understand the theory of elementary particles, imagine a large city made entirely of bricks. This city is filled with buildings of all shapes and sizes. Every one of them, and the streets as well, have been constructed with only a few different types of brick. If we substitute universe for city and particle for brick, we have the theory of elementary particles. It was the study of elementary particles that brought physicists nose to nose with the most devastating, to a physicist, discovery. Newtonian physics does not work in the realm of the very small. The impact of that earth-shaking discovery still is reshaping our world view. Quantum mechanical experiments repeatedly produced results which the physics of Newton could neither predict nor explain. Yet, although Newton's physics could not account for phenomena in the microscopic realm, it continued to explain microscopic phenomena very well, even though the macroscopic is made of the microscopic. This was perhaps the most profound discovery of science. Newton's laws are based upon observations of the everyday world. They predict events, and these events pertain to real things like baseballs and bicycles. Quantum mechanics is based upon experiments conducted in the subatomic realm. It predicts probabilities. These probabilities pertain to subatomic phenomena. Subatomic phenomena cannot be observed directly. None of our senses can detect them. Not only has no one ever seen an atom, much less an electron, no one has ever tasted, touched, heard, or smelled one either. Newton's laws depict events which are simply to understand and easy to picture. Quantum mechanics depicts the probabilities of phenomena which defy conceptualization and are impossible to visualize. Therefore, these phenomena must be understood in a way that is not more difficult than our usual way of understanding, but different from it. Do not try to make a complete mental picture of quantum mechanical events. Physicists make partial pictures of quantum phenomena, but even these pictures have a questionable value. Instead, allow yourself to be open without making an effort to visualize anything. Werner Heisenberg, one of the founders of quantum physics, wrote, "The mathematically formulated laws of quantum theory show clearly that our ordinary intuitive concepts cannot be unambiguously applied to the smallest particles. All the words or concepts we use to describe ordinary physical objects, such as position, velocity, color, size, and so on, become indefinite and problematic if we try to use them of elementary particles." The idea that we do not understand something until we have a picture of it in our heads is a byproduct of the Newtonian way of looking at the world. If we want to get past Newton, we have to get past that. The ability to predict the future based on a knowledge of the present and the laws of motion gave our ancestors a power they had never known. However, these concepts carry within them a very dispiriting logic. If the laws of nature determine the future of an event, then given enough information, we could have predicted our present at some time in the past. That time in the past also could have been predicted at a time still earlier. In short, if we are to accept the mechanistic determination of Newtonian physics, if the universe really is a great machine, then from the moment that the universe was created and set into motion, everything that was to happen in it already was determined. According to this philosophy, we may seem to have a will of our own and the ability to alter the course of events in our lives, but we do not. Everything from the beginning of time has been predetermined, including our illusion of having a free will. The universe is a pre-recorded tape, playing itself out in the only way that it can. The status of men is immeasurably more dismal than it was before the advent of science. The great machine runs blindly on, and all things in it are but cogs. According to quantum mechanics, however, it is not possible, even in principle, to know enough about the present to make a complete prediction about the future. Even if we have the best possible measuring devices, it is not possible. It is not a matter of the size of the task or the inefficiency of detectors. The very nature of things is such that we must choose which aspect of them we wish to know best, for we can know only one of them with precision. As Niels Bohr, another founder of quantum mechanics, put it, in quantum mechanics we are not dealing with an arbitrary renunciation of a more detailed analysis of atomic phenomena, but with a recognition that such an analysis is in principle included. For example, imagine an object moving through space. It has both a position and a momentum which we can measure. This is an example of the old Newtonian physics. Momentum is a combination of how big an object is, how fast it is going, and the direction that it is moving. And since we can determine both the position and the momentum of the object at a particular time, it is not a very difficult affair to calculate where it will be at some point in the future. If we can see an airplane flying north at 200 miles per hour, we know that in 1 hour it will be 200 miles farther north if it does not change its course or speed. The mind-expanding discovery of quantum mechanics is that Newtonian physics does not apply to subatomic phenomena. In the subatomic realm, we cannot know both the position and the momentum of a particle with absolute precision. We can know both approximately, but the more we know about one, the less we know about the other. We can know either of them precisely, but in that case we can know nothing about the other. And this is Werner Heisenberg's uncertainty principle. As incredible as it seems, it has been verified repeatedly by experiment. Of course, if we picture a moving particle, it is very difficult to imagine not being able to measure both its position and momentum. Not to be able to do so defies our common sense. This is not the only quantum mechanical phenomenon which contradicts common sense. Common sense contradictions, in fact, are at the heart of the new physics. They tell us again and again that the world may not be what we think it is. It may be much, much more. Since we cannot determine both the position and momentum of subatomic particles, we cannot predict much about them. Accordingly, quantum mechanics does not and cannot predict specific events. It does, however, predict probabilities. Probabilities are the odds that something is going to happen or that it is not going to happen. Quantum theory can predict the probability of a microscopic event with the same precision that Newtonian physics can predict the actual occurrence of a macroscopic event. Newtonian physics says, if such and such is the case now, then such and such is going to happen next. Quantum mechanics says, if such and such is the case now, then the probability that such and such is going to happen next is whatever it is calculated to be. We never can know with certainty what will happen to the particle that we are observing. All that we can know for sure are the probabilities for it to behave in certain ways. And this is the most that we can know because the two data which must be included in a Newtonian calculation, position and momentum, cannot both be known with precision. We must choose by the selection of our experiment which one we want to measure most accurately. The lesson of Newtonian physics is that the universe is governed by laws that are susceptible to rational understanding. By applying these laws, we extend our knowledge of and therefore our influence over our environment. Newton was a religious person. He saw his laws as manifestations of God's perfection. Nonetheless, Newton's laws served man's cause well. They enhanced his dignity and vindicated his importance in the universe. Following the Middle Ages, the new field of science, natural philosophy, came like a fresh breeze to revitalize the spirit. It is ironic that in the end, natural philosophy reduced the status of men to that of helpless cogs in a machine whose functioning had been preordained from the day of its creation. Contrary to Newtonian physics, quantum mechanics tells us that our knowledge of what governs events on the subatomic level is not nearly what we assumed it would be. It tells us that we cannot predict subatomic phenomena with any certainty. We only can predict their probabilities. Philosophically, however, the implications of quantum mechanics are psychedelic. Not only do we influence our reality, but in some degree, we actually create it. Because it is the nature of things that we can know either the momentum of a particle or its position, but not both. We must choose which of these two properties we want to determine. Metaphysically, this is very close to saying that we create certain properties because we choose to measure those properties. Said another way, it is possible that we create something that has position, for example, like a particle, because we are intent on determining position, and it is impossible to determine position without having something occupying the position that we want to determine. Quantum physicists ponder questions like, did a particle with position exist before we conducted an experiment to measure its position? And did any particles exist at all before we thought about them and measured them? Did we create the particles that we are experimenting with? Incredible as it sounds, this is a possibility that many physicists recognize. John Wheeler, a well-known physicist at Princeton, wrote, "May the universe in some strange sense be brought into being by the participation of those who participate? The vital act is the act of participation. Participator is the incontrovertible new concept given by quantum mechanics. It strikes down the term observer of classical theory, the man who stands safely behind the thick glass wall and watches what goes on without taking part. It can't be done, quantum mechanics says." The languages of Eastern mystics and Western physicists are becoming very similar. Newtonian physics and quantum mechanics are partners in a double irony. Newtonian physics is based upon the idea of laws which govern phenomena and the power inherent in understanding them, but it leads to impotence in the face of a great machine, which is the universe. Quantum mechanics is based upon the idea of minimal knowledge of future phenomena. We are limited to knowing probabilities. But it leads to the possibility that our reality is what we choose to make it. There is another fundamental difference between the old physics and the new physics. The old physics assumes that there is an external world which exists apart from us. It further assumes that we can observe, measure, and speculate about the external world without changing it. According to the old physics, the external world is indifferent to us and to our needs. Galileo's historical stature stems from his tireless and successful efforts to quantify, measure the phenomena of the external world. And there is great power inherent in the process of quantification. For example, once a relationship is discovered, like the rate of acceleration of a falling object, it matters not who drops the object, what object is dropped, or where the dropping takes place. The results are always the same. An experimenter in Italy gets the same results as a Russian experimenter who repeats the experiment a century later. The results are the same whether the experiment is done by a skeptic, a believer, or a curious bystander. Facts like these convinced philosophers that the physical universe goes unheedingly on its way, doing what it must, without regard for its inhabitants. For example, if we simultaneously drop two people from the same height, it is a verifiable, repeatable fact that they both will hit the ground at the same time, regardless of their weights. We can measure their fall, acceleration, and impact the same way that we measure the fall, acceleration, and impact of stones. In fact, the results will be the same as if they were stones. But there is a difference between people and stones, you might say. Stones have no opinions or emotions. People have both. One of these dropped people, for example, might be frightened by his experience, and the other might be angry. Don't their feelings have any importance in this scheme? No. The feelings of our subjects matter not in the least. When we take them up the tower again, struggling this time, and drop them off again, they fall with the same acceleration and duration that they did the first time, even though now, of course, they are both fighting mad. The great machine is impersonal. In fact, it was precisely this impersonality that inspired scientists to strive for absolute objectivity. The concept of scientific objectivity rests upon the assumption of an external world, which is out there, as opposed to an I, which is in here. This way of perceiving, which puts other people out there, makes it very lonely in here. According to this view, nature in all her diversity is out there. The task of the scientist is to observe the out there as objectively as possible. To observe something objectively means to see it as it would appear to an observer who has no prejudices about what he observes. The problem that went unnoticed for 3 centuries is that a person who carries such an attitude certainly is prejudiced. His prejudice is to be objective, that is, to be without a performed opinion. In fact, it is impossible to be without an opinion. An opinion is a point of view. The point of view that we can be without a point of view is a point of view. The decision itself to study one segment of reality instead of another is a subjective expression of the researcher who makes it. It affects his perceptions of reality, if nothing else. Since reality is what we are studying, the matter gets very sticky here. The new physics, quantum mechanics, tells us clearly that it is not possible to observe reality without changing it. If we observe a certain particle collision experiment, not only do we have no way of proving that the result would have been the same if we had not been watching it, all that we know indicates that it would not have been the same because the result that we got was affected by the fact that we were looking for it. Some experiments show that light is wave-like. Other experiments show equally well that light is particle-like. If we want to demonstrate that light is a particle-like phenomenon, or that light is a wave-like phenomenon, we only need to select the appropriate experiment. According to quantum mechanics, there is no such thing as objectivity. We cannot eliminate ourselves from the picture. We are a part of nature. And when we study nature, there is no way around the fact that nature is studying itself. Physics has become a branch of psychology, or perhaps the other way around. Carl Jung, the Swiss psychologist, wrote, "The psychological rule says that when an inner situation is not made conscious, it happens outside, as fate. That is to say, when the individual remains undivided and does not become conscious of his inner contradictions, the world must perforce act out the conflict and be torn into opposite halves." Jung's friend, the Nobel Prize-winning physicist Wolfgang Pauli, put it this way: "From an inner center, the psyche seems to move outward, in the sense of an extraversion into the physical world." If these men are correct, then physics is the study of the structure of consciousness. The descent downward from the macroscopic level to the microscopic level, which we have been calling the realm of the very small, is a two-step process. The first step downward is to the atomic level. The second step downward is to the subatomic level. The smallest object that we can see, even under a microscope, contains millions of atoms. To see the atoms in a baseball, we would have to make the baseball the size of the Earth. If a baseball were the size of the Earth, its atoms would be about the size of grapes. If you can picture the Earth as a huge glass ball filled with grapes, that is approximately how a baseball full of atoms would look. The step downward from the atomic level takes us to the subatomic level, and here we find the particles that make up atoms. The difference between the atomic level and the subatomic level is as great as the difference between the atomic level and the world of sticks and rocks. It would be impossible to see the nucleus of an atom the size of a grape. In fact, it would be impossible to see the nucleus of an atom the size of a room. To see the nucleus of an atom, the atom would have to be as high as a 14-story building. The nucleus of an atom as high as a 14-story building would be about the size of a grain of salt. Since a nuclear particle has about 2,000 times more mass than an electron, the electrons revolving around this nucleus would be about as massive as dust particles. The dome of St. Peter's Basilica in the Vatican has a diameter of about 14 stories. Imagine a grain of salt in the middle of the dome of St. Peter's, with a few dust particles revolving around it at the outer edges of the dome. This gives us the scale of subatomic particles. It is in this realm, the subatomic realm, that Newtonian physics has proven inadequate and that quantum mechanics is required to explain particle behavior. A subatomic particle is not a particle like a dust particle. There is more than a difference in size between a dust particle and a subatomic particle. A dust particle is a thing, an object. A subatomic particle cannot be pictured as a thing. Therefore, we must abandon the idea of a subatomic particle as an object. Quantum mechanics views subatomic particles as tendencies to exist, or tendencies to happen. How strong these tendencies are is expressed in terms of probabilities. A subatomic particle is a quantum, which means a quantity of something. What that something is, however, is a matter of speculation. Many physicists feel that it is not meaningful even to pose the question. It may be that the search for the ultimate stuff of the universe is a crusade for an illusion. At the subatomic level, mass and energy change unceasingly into each other. Particle physicists are so familiar with the phenomena of mass becoming energy and energy becoming mass that they routinely measure the mass of particles in energy units. Since the tendencies of subatomic phenomena to become manifest under certain conditions are probabilities, this brings us to the matter, no pun, of statistics. Because there are millions and millions of subatomic particles in the smallest space that we can see, it is convenient to deal with them statistically. Statistical descriptions are pictures of crowd behavior. Statistics cannot tell us how one individual in a crowd will behave, but they can give us a fairly accurate description based on repeated observations of how a group as a whole behaves. For example, a statistical study of population growth may tell us how many children were born in each of several years and how many are predicted to be born in years to come. However, the statistics cannot tell us which families will have the new children and which ones will not. If we want to know the behavior of traffic at an intersection, we can install devices there to gather data. The statistics that these devices provide may tell us how many cars, for instance, turn left during certain hours, but not which cars. Statistics is used in Newtonian physics. It is used, for example, to explain the relationship between gas volume and pressure. This relation is named Boyle's law after its discoverer, Robert Boyle, who lived in Newton's time. It could as easily be known as the bicycle pump law, as we shall see. Boyle's law says that if the volume of a container holding a given amount of gas at any constant temperature is reduced by 1/2, the pressure exerted by the gas in the container doubles. Imagine a person with a bicycle pump. He has pulled the plunger fully upward and is about ready to push it down. The hose of the pump is connected to a pressure gauge instead of to a bicycle tire so that we can see how much pressure is in the pump. And since there is no pressure on the plunger, there's no pressure in the pump cylinder, and the gauge reads 0. However, the pressure inside the pump is not actually 0. We live at the bottom of an ocean of air, our atmosphere. The weight of the several miles of air above us exerts a pressure at sea level of 14.7 pounds on every square inch of our bodies. Our bodies do not collapse because they are exerting 14.7 pounds per square inch outward. This is the state that we usually read as 0 on a bicycle pressure gauge. To be accurate, suppose that we set our gauge to read 14.7 pounds per square inch before we push down on the pump handle. Now, we push the piston down halfway. The interior volume of the pump cylinder is now 1/2 of its original size, and no air has been allowed to escape because the hose is connected to a pressure gauge. The gauge now reads 29.4 pounds per square inch, or twice the original pressure. Next, we push the plunger 2/3 of the way down. The interior volume of the pump cylinder is now 1/3 of its original size, and the pressure gauge reads 3 times the original pressure, 44.1 pounds per square inch. This is Boyle's law. At a constant temperature, the pressure of a quantity of gas is inversely proportional to its volume. If the volume is reduced to 1/2, the pressure doubles. If the volume is reduced to 1/3, the pressure triples, etc. To explain why this is so, we come to classical statistics. The air, a gas in our pump, is composed of millions of molecules. Molecules are made of atoms. These molecules are in constant motion, and at any given time, millions of them are banging into the pump walls. Although we do not detect each single collision, the macroscopic effect of these millions of impacts on a square inch of the pump wall produces the phenomenon of pressure on it. If we reduce the volume of the pump cylinder by 1/2, we crowd the gas molecules into a space twice as small as the original one, thereby causing twice as many impacts on the same square inch of pump wall. The macroscopic effect of this is a doubling of the pressure. By crowding the molecules into 1/3 of the original space, we cause 3 times as many molecules to bang into the same square inch of pump wall, and the pressure on it triples. This is the kinetic theory of gases. In other words, pressure results from the group behavior of a large number of molecules in motion. It is a collection of individual events. Each individual event can be analyzed because, according to Newtonian physics, each individual event is theoretically subject to deterministic laws. In principle, we can calculate the path of each molecule in the pump chamber. This is how statistics is used in the old physics. Quantum mechanics also used statistics, but there's a very big difference between quantum mechanics and Newtonian physics. In quantum mechanics, there is no way to predict individual events. This is the startling lesson that experiments in the subatomic realm have taught us. The scientific idea of truth, traditionally, had been anchored in an absolute truth somewhere out there. That is, an absolute truth with an independent existence. The closer that we came in our approximations to the absolute truth, the truer our theories were said to be, although we might never be able to perceive the absolute truth directly, or to open the watch, as Einstein put it. Still, we tried to construct theories such that for every facet of absolute truth, there was a corresponding element in our theories. The Copenhagen interpretation was the first consistent formulation of quantum mechanics. Einstein opposed it in 1927, and he argued against it until his death, although he, like all physicists, was formed to acknowledge its advantages in explaining subatomic phenomena. The Copenhagen interpretation says, in effect, that it does not matter what quantum mechanics is about. The important thing is that it works in all possible experimental situations. And this is one of the most important statements in the history of science. The Copenhagen interpretation of quantum mechanics began a monumental reunion, which was all but unnoticed at the time. The rational part of our psyche, typified by science, began to merge again with that other part of us, which we had ignored since the 1700s, our irrational side. The scientific idea of truth traditionally had been anchored in an absolute truth somewhere out there, that is, an absolute truth with an independent existence. The closer that we came in our approximations to the absolute truth, the truer our theories were said to be. Although we might never be able to perceive the absolute truth directly or to open the watch, as Einstein put it, still we tried to construct theories such that for every facet of absolute truth, there was a corresponding element in our theories. The Copenhagen interpretation does away with this idea of a one-to-one correspondence between reality and theory. This is another way of saying what we've said before. Quantum mechanics discards the laws governing individual events and states directly the laws governing aggregations. It is very pragmatic. The philosophy of pragmatism goes something like this. The mind is such that it deals only with details. It is not possible for the mind to relate to anything other than ideas. Therefore, it is not correct to think that the mind actually can ponder reality. All that the mind can ponder is its ideas about reality. Whether or not that is the way reality actually is a metaphysical issue. Therefore, whether or not something is true is not a matter of how closely it corresponds to the absolute truth, but of how consistent it is with our experience. The extraordinary importance of the Copenhagen interpretation lies in the fact that for the first time, scientists attempting to formulate a consistent physics were forced by their own findings to acknowledge that a complete understanding of reality lies beyond the capabilities of rational thought. It was this that Einstein could not accept. The most incomprehensible thing about the world, he wrote, is that it is comprehensible. But the deed was done. The new physics was based not upon absolute truth, but upon us. Henry Pierce Stapp, a physicist at the Lawrence Berkeley Laboratory, expressed this eloquently. The Copenhagen interpretation of quantum mechanics was essentially a rejection of the presumption that nature could be understood in terms of elementary space-time realities. According to the new view, the complete description of nature at the atomic level was given by probability functions that referred not to underlying microscopic space-time realities, but rather to the macroscopic objects of sense experience. The theoretical structure did not extend down and anchor itself on fundamental microscopic space-time realities. Instead, it turned back and anchored itself in the concrete sense realities that form the basis of social life. This pragmatic description is to be contrasted with descriptions that attempt to peer behind the scenes and tell us what is really happening. Another way of understanding the Copenhagen interpretation, in retrospect, is in terms of split brain analysis. The human brain is divided into two halves, which are connected at the center of the cerebral cavity by a tissue. To treat certain conditions, such as epilepsy, the two halves of the brain sometimes are separated surgically. From the experiences reported by and the observations made of persons who have undergone this surgery, we have discovered a remarkable fact. Generally speaking, the left side of our brain functions in a different manner than the right side. Each of our two brains sees the world in a different way. The left side of our brain perceives the world in a linear manner. It tends to organize sensory input into the form of points on a line, with some points coming before others. For example, language, which is linear. The words which you are reading flow along a line from left to right, is a function of the left hemisphere. The left hemisphere functions logically and rationally. It is the left side of the brain which creates the concept of causality, the image that one thing causes another because it always precedes it. The right hemisphere, by comparison, perceives whole patterns. Persons who have had split brain operations actually have two separate brains. When each hemisphere is tested separately, it is found that the left brain remembers how to speak and use words, while the right brain generally cannot. However, the right brain remembers the lyrics of songs. The left side of our brain tends to ask certain questions of its sensory input. The right side of our brain tends to accept what is given more freely. Roughly speaking, the left hemisphere is rational, and the right hemisphere is irrational. Physiologically, the left hemisphere controls the right side of the body, and the right hemisphere controls the left side of the body. In view of this, it is no coincidence that both literature and mythology associate the right hand, left hemisphere, with rational, male, and assertive characteristics, and the left hand, right hemisphere, with mystical, female, and receptive characteristics. The Chinese wrote about the same phenomena thousands of years ago, yin and yang, although they were not known for their split brain surgery. Our entire society reflects a left hemispheric bias. It is rational, masculine, and assertive. It gives very little reinforcement to those characteristics representative of the right hemisphere, intuitive, feminine, and receptive. The advent of science marks the beginning of the ascent of left hemispheric thinking into the dominant mode of Western cognition, and the descent of right hemispheric thinking into the underground, under-psyche status, from which it did not emerge with scientific recognition until Freud's discovery of the unconscious, which of course he labeled dark, mysterious, and irrational, because that is how the left hemisphere views the right hemisphere. The Copenhagen interpretation was in effect a recognition of the limitations of left hemispheric thought, although the physicists at Brussels in 1927 could not have thought in those terms. It was also a recognition of those psychic aspects which long had been ignored in a rationalistic society. After all, physicists are essentially people who wonder at the universe. To stand in awe and wonder is to understand in a very specific way, even if that understanding cannot be described. The subjective experience of wonder is a message to the rational mind that the object of wonder is being perceived and understood in ways other than the rational. The next time you are awed by something, let the feeling flow freely through you, and do not try to understand it. You will find that you do understand, but in a way that you will not be able to put into words. You are perceiving intuitively through your right hemisphere. It has not atrophied from lack of use, but our skill in listening to it has been dulled by 3 centuries of neglect. Wu Li masters perceive in both ways, the rational and the irrational, the assertive and the receptive, the masculine and the feminine. They reject neither one nor the other. They only dance. Dancing lessons for Newtonian physics. Dancing lesson for quantum mechanics. Can picture it, cannot picture it. Based on ordinary sense perceptions. Based on behavior of subatomic particles in systems not directly observable. Describes things, individual objects in space and their changes in time. Describes statistical behavior of systems. Predicts events, predicts probabilities, assumes an objective reality out there, does not assume an objective reality apart from our experience. We can observe something without changing it. We cannot observe something without changing it. Claims to be based on absolute truth, the way that nature really is behind the scenes, claims only to correlate experience correctly. This is quantum mechanics. The next question is, how does it work? Part 1. Patterns of organic energy. Living. When we talk of physics as patterns of organic energy, the word that catches our attention is organic. Organic means living. Most people think that physics is about things that are not living, such as pendulums and billiard balls. This is a common point of view, even among physicists, but it is not as evident as it may seem. Let us explore this viewpoint with the aid of a hypothetical person, a young man named Jim DeWitt, who is the perpetual champion of the non-obvious. It is not at all true, says Jim DeWitt, that physics is about non-living things. This is evident from our discussion of falling bodies. Even if some of them are the humankind, they all accelerate at the same rate in a vacuum. So physics does apply to living things. But that is an unfair example, we say. Rocks have no choice in the matter of falling. If we drop them, they fall. If we don't drop them, they don't fall. Humans, on the other hand, exercise choice. Accidents excluded, humans ordinarily are not found in the act of falling. Why? Because they know that falling may hurt them, and they have no desire to be hurt. In other words, humans process information, they know that they may be hurt, and they respond to it by not falling. Rocks can do neither. That is the way things appear, says DeWitt, but it may not be the way they actually are. For example, by watching time-lapse photography, we know that plants often respond to stimuli with human-like reactions. They retreat from pain, advance toward pleasure, and even languish in the absence of affection. The only difference is that they do it at a much slower rate than we do. So much slower, in fact, that it appears to the ordinary perception that they do not react at all. If this is so, then how can we say with certainty that rocks and even mountain ranges do not react also as living organisms, but with a reaction time so slow that to catch it with time-lapse photography would require millennia between exposures? Of course, there's no way to prove this, but there is no way of disproving it either. The distinction between living and non-living is not so easy to make. That's clever, we think. But from a practical point of view, it cannot be observed that inert matter responds to stimuli, and there is no question that humans do. Wrong again, says DeWitt, reading our thoughts. Any chemist can verify that most chemicals, which usually come out of the ground as rocks, do react to stimulation. Under the right conditions, for example, sodium reacts to chlorine by forming sodium chloride, salt. Iron reacts to oxygen by forming iron oxides, rust, and so on, just as humans react to food when they are hungry and to affection when they are lonely. Well, this is so, we admit, but it hardly seems fair to compare a chemical reaction to a human reaction. A chemical reaction either happens or it does not happen. There is nothing in between. When two such chemicals are combined properly, they react. If they are not properly combined, they do not react. Humans are much more complex. If we offer food to a hungry person, he might eat it or he might not, depending upon his circumstances. And if he eats it, he might eat his fill or he might not, considering the person who is hungry and late for an appointment. If the appointment is important enough, he will go without eating, even though he is hungry. If a person knows that his food is poisonous, he will not eat, even though he is hungry. It is a matter of processing information and responding appropriately that distinguishes a human reaction from a chemical reaction. Chemicals have no options. They always must act one way or the other. Of course, beams Jim DeWitt. But how do we know that our responses are not as rigidly pre-programmed as those of a chemical, with the only difference being that our programs are enormously more complex? We may not have any more freedom of action than stones do, although unlike stones, we deceive ourselves into thinking that we do. We have no way to dispute this argument. DeWitt has shown us the arbitrary quality of our prejudices. We would like to think that we are different from stones because we are living and they are not, but there is no way we can prove our position or disprove this. We cannot establish clearly that we are different from inorganic substances. That means that, logically, we must admit that we may not be alive. Since this is absurd, the only alternative is to admit that inanimate objects may be living. The distinction between organic and inorganic is a conceptual prejudice. It becomes even harder to maintain as we advance into quantum mechanics. Something is organic, according to our definition, if it can respond to processed information. The astounding discovery awaiting newcomers to physics is that the evidence gathered in the development of quantum mechanics indicates that subatomic particles constantly appear to be making decisions. More than that, the decisions they seem to make are based on decisions made elsewhere. Subatomic particles seem to know instantaneously what decisions are made elsewhere, and elsewhere can be as far away as another galaxy. The key word is instantaneously. How can a subatomic particle over here know what decision another particle over there has made at the same time the particle over there makes it? All the evidence belies the fact that quantum particles are actually particles. A particle, as we mentally picture it, classically defined, is a thing which is confined to a region in space. It is not spread out. It is either here or it is there, but it cannot be both here and there at the same time. A particle over here can communicate with a particle over there by shouting at it, sending it a TV picture, waving, etc. But that takes time, even if only milliseconds. If the two particles are in different galaxies, it could take centuries. For a particle here to know what is going on over there while it is happening, it must be over there. But if it is over there, it cannot be here. If it is both places at once, then it is no longer a particle. This means that particles may not be particles at all. It also means that these apparent particles are related with other particles in a dynamic and intimate way that coincides with our definition of organic. Some biologists believe that a single plant cell carries within it the capability to reproduce the entire plant. Similarly, the philosophical implication of quantum mechanics is that all of the things in our universe, including us, that appear to exist independently are actually parts of one all-encompassing organic pattern, and that no parts of that pattern are ever really separate from it or from each other. To understand these decisions and what makes them, let us start with a discovery made in 1900 by Max Planck. This year generally is considered the birthday of quantum mechanics. In December of that year, Planck reluctantly presented to the scientific community a paper which was to make him famous. He himself was displeased with the implications of his paper, and he hoped that his colleagues could do what he could not do, explain its contents in terms of Newtonian physics. He knew in his heart, however, that they could not, and that neither could anyone else. He also sensed, and correctly so, that his paper would shift the very foundations of science. What had Planck discovered that disturbed him so much? Planck had discovered that the basic structure of nature is granular, or, as physicists like to say, discontinuous. What is meant by discontinuous? If we talk about the population of a city, it is evident that it can fluctuate only by a whole number of people. The least the population of a city can increase or decrease is by one person. It cannot increase by 0.7 of a person. It can increase or decrease by 15 people, but not by 15.27 people. In the dialect of physics, a population can change only in discrete increments, or discontinuously. It can get larger or smaller only in jumps, and the smallest jump that it can make is a whole person. In general, this is what Planck discovered about the processes of nature. Planck did not intend to undermine the foundations of Newtonian physics. He was a conservative German physicist. Rather, he inadvertently fathered the revolution of quantum mechanics by attempting to solve a specific problem, dealing with energy radiation. Planck was searching for an explanation of why things behave as they do when they get hot. Namely, he wanted to know how objects glow brighter as they get hotter and change color when the temperature is increased or decreased. Classical physics, which successfully had unified such diverse fields as acoustics, optics, and astronomy, which had all but satiated the scientific appetite, which had unraveled the enigmas of the universe and rearranged them in neat packages, held no sensible explanation of this commonplace phenomenon. It was, to use the parlance of the day, one of the few clouds on the horizon of classical physics. In 1900, physicists pictured the atom as a nucleus that looked something like a plum, to which were attached tiny protruding springs. This was before the planetary model of the atom. At the end of each spring was an electron, and giving the atom a jolt by heating it, for instance, caused its electrons to jiggle, oscillate, on the ends of their springs. The jiggling electrons were thought to give off radiant energy, and this was thought to account for the fact that hot objects glow. An accelerating electrical charge creates electromagnetic radiation. An electron carries an electrical charge, negative, and if it is jiggling, it is accelerating, first in one direction and then in the other. Physicists thought that heating the atoms in a metal caused them to become agitated, and this in turn caused their electrons to jiggle up and down and emit light in the process. The energy that the atom absorbed when it was jolted, or heated, the theory went, was radiated by the jiggling electrons. You can substitute atomic oscillators if your friends won't take jiggling electrons seriously. This same theory also claimed that the energy absorbed by an atom was distributed equally to its oscillators, or electrons, and that those electrons which oscillated or jiggled at higher frequencies, faster, radiated their energy most efficiently. Unfortunately, this theory didn't work. It proved some very incorrect things. First, it proved that all heated objects emit more high-frequency light, blue, violet, than low-frequency light, red. In other words, even moderately hot objects, according to this classical theory, emit an intense blue-white color, just like objects which are white-hot, but in lesser amounts. This is incorrect. Moderately hot objects emit primarily red light. Second, the classical theory proved that highly heated objects radiate infinite amounts of high-frequency light. This is incorrect. Highly heated objects emit a finite amount of high-frequency light. Do not be concerned with high frequencies and low frequencies. These terms will be explained shortly. The point is that Planck was exploring one of the last major problems of classical physics, its erroneous predictions concerning energy radiation. Physicists dubbed this problem the ultraviolet catastrophe. Although it sounds like a rock band, the ultraviolet catastrophe reflected a real concern with the fact that heated objects do not radiate large amounts of energy in the form of ultraviolet light, the highest frequency light known in 1900, the way the classical theory predicted. The name of the phenomenon that Planck was studying is black-body radiation. Black-body radiation is the radiation that comes from a non-reflecting, perfectly absorbing, flat, non-glossy, black body. Since black is the absence of color, no light is reflected or emitted, black bodies have no color unless we heat them. If a black body is glowing a certain color, we know that it is because of the energy that we have added to it and not because it reflects or emits that color spontaneously. A black body does not always mean a solid body that is black. Suppose that we have a metal box that is completely sealed except for a small hole. If we look inside, what do we see? Nothing, because there is no light in there. A little light may come in through the hole, but not that much. Now, suppose that we heat the box until it glows red, and then look through the hole. What do we see? Red. Who said physics is hard? This is the kind of phenomenon that Planck studied. All the physicists in 1900 assumed that after the electrons of an excited atom began to jiggle, they radiated their energy smoothly and continuously until they ran down and their energy was dissipated. Planck discovered that excited atomic oscillators do not do this. They emit and absorb energy only in specific amounts. Instead of radiating energy smoothly and continuously like a clock spring runs down, they radiate their energy in spurts, dropping to a lower energy level after each spurt until they stop oscillating altogether. In short, Planck discovered that the changes of nature are explosive, not continuous and smooth. Planck was the first physicist to talk about energy packets and quantized oscillators. He sensed that he had made a major discovery, one which ranked with the discoveries of Newton, and he was right. The philosophy and paradigms of physics never were to be the same, although it took another 27 years for quantum mechanics to take form. It is difficult today to understand how bold was Planck's theory of quanta. Victor Guillemin, professor of physics at Harvard, put it this way. Planck had to make a radical and seemingly absurd assumption, for according to classical laws, and common sense as well, it had been presumed that an electronic oscillator, once set in motion by a jolt, radiates its energy smoothly and gradually while its oscillatory motion subsides to rest. Planck had to assume that the oscillator ejects its radiation in sudden spurts, dropping to lesser amplitudes of oscillation with each spurt. He had to postulate that the energy of motion of each oscillator can neither build up nor subside smoothly and gradually, but may change only in sudden jumps. In a situation where energy is being transferred to and fro between the oscillators and the light waves, the oscillators must not only emit but also absorb radiant energy in discrete packets. He coined the name quanta for the packets of energy, and he spoke of the oscillators as being quantized. Thus, the trenchant concept of the quantum entered physical science. Planck is not the only father of quantum mechanics. He's also the discoverer of Planck's constant. Planck's constant is a certain number which never changes. It is used to calculate the size of the energy packets, or quanta, of each light frequency, color. The energy in each light quantum of a particular color is the frequency of the light multiplied by Planck's constant. All of the energy packets of each color have the same amount of energy. All of the energy packets of red light, for example, are the same size. All of the energy packets of green light are the same size. All of the energy packets of violet light are the same size. The energy packets of violet light, however, are larger than the energy packets of green light, and the energy packets of green light are larger than the energy packets of red light. In other words, Planck discovered that energy is absorbed and emitted in little chunks, and that the size of the chunks of a low-frequency light, like red, is smaller than the size of the chunks of a high-frequency light, like violet. And this explains why hot objects radiate energy as they do. What Einstein had to say about space and time is that there is no such thing as space and time. There is only space-time. Space-time is a continuum. A continuum is something whose parts are so close together, so arbitrarily small, that the continuum really cannot be broken down into them. There are no breaks in a continuum. It is called a continuum because it flows continuously. For example, a one-dimensional continuum is a line drawn on a wall. Theoretically, we might say that the line is comprised of a series of points, but the points are each infinitely close to one another. The result is that the line flows continuously from one end of it to the other. An example of a two-dimensional continuum is the wall. It has two dimensions, length and width. Similarly, all of the points on the wall are in contact with other points on the wall, and the wall itself is a continuous surface. A three-dimensional continuum is what we commonly call space. A pilot flying his airplane navigates in a three-dimensional continuum. To give his location, he must state, for example, not only how far north and how far east of a given point he is, but he also must report his altitude. The airplane itself, like all things physical, is three-dimensional. It has a width, a height, and a depth. And this is why mathematicians call our reality, their reality too, three-dimensional. According to Newtonian physics, our three-dimensional reality is separate from and moves forward in a one-dimensional time. Not so, says the special theory of relativity. Our reality is four-dimensional, and the fourth dimension is time. We live, breathe, and exist in a four-dimensional space-time continuum. The Newtonian view of space and time is a dynamic picture. Events develop with the passage of time. Time is one-dimensional and moves forward. The past, present, and future happen in that order. The special theory of relativity, however, says that it is preferable and more useful to think in terms of a static, non-moving picture of space and time. This is the space-time continuum. In this static picture, the space-time continuum, events do not develop. They just are. If we could view our reality in a four-dimensional way, we would see that everything that now seems to unfold before us with the passing of time already exists in toto, painted, as it were, on the fabric of space-time. We would see all, the past, the present, and the future with one glance. Of course, this is only a mathematical proposition, isn't it? Don't worry about visualizing a four-dimensional world. Physicists can't do it either. For the moment, just assume that Einstein might be right, since the evidence so far suggests that he is. His message is that space and time are related in an intimate manner. For lack of a better way of saying it, he expressed this relationship by calling time a fourth dimension. Fourth dimension is a translation from one language to another. The original language is mathematics, and the second language is English. The problem is that there is simply no way of precisely expressing what the first language says in terms of the second language. Therefore, time as a fourth dimension is merely a label that we give to a relationship. The relationship in question is the relationship between space and time as it is expressed mathematically in the theories of relativity. The relationship between space and time that Einstein discovered is similar to the relationship between the sides of a right triangle, which Pythagoras, the Greek, a contemporary of Confucius, discovered about 550 BC. A right triangle is a triangle that contains a right angle. A right angle is formed whenever two perpendicular lines intersect. Below is a right triangle. The side of a right triangle that is opposite the right angle is called the hypotenuse. The hypotenuse is always the longest side of a right triangle. Pythagoras discovered that as long as we know the length of the two shorter sides of a right triangle, we can calculate the length of the longest side. This relationship expressed mathematically is the Pythagorean theorem. The first leg squared plus the second leg squared equals the hypotenuse squared. A hypotenuse of a given length can be calculated from many different combinations of shorter legs. In other words, there are many combinations of different size legs that all calculate to have the same hypotenuse. For example, the first leg might be very short and the second leg very long, or the other way around, or anything in between. If we substitute space for one of the legs of a right triangle, time for the other leg, and space-time, interval, for the hypotenuse, we have a relationship which is conceptually analogous to the relationship between space, time, and the space-time interval described in the special theory of relativity. The space-time interval between two events is an absolute. It never varies. It can appear differently to observers in different states of motion, but it is itself invariant. The special theory of relativity shows how observers in different frames of reference can observe the same two events and calculate the space-time interval between them. The answer that all of the observers get will be the same. One observer may be in a state of motion such that for him there is a time and a distance involved between the two events, and another observer may be in a state of motion such that his measuring devices indicate a different distance and a different time between the events. But the space-time interval between the two events does not vary. For example, the space-time interval, the absolute separation between two exploding stars, is the same whether it is viewed from a slow-moving frame of reference, like a planet, or from a fast-moving frame of reference, like a speeding rocket. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Minkowski's mathematical explorations of space and time were both revolutionary and fascinating. Out of them came a simple diagram of space-time, showing the mathematical relationship of the past, present, and the future. Of the wealth of information contained in this diagram, the most striking is that all of the past and all of the future for each individual meet and forever meet at one single point: now. Furthermore, the now of each individual is specifically located and will never be found in any other place than here, wherever the observer is at. 63 years before Ram Dass's great book, Be Here Now, established the watchwords of the awareness movement, Hermann Minkowski proved that in physical reality no choice exists in the matter. Pun. Unfortunately for physicists, the realization is not always the experience. Nonetheless, after 2,000 years of use in the East, Being Here Now, the beginning step in meditation, received the validation of Western science via Minkowski's rigorous mathematical confirmation of it, inspired by the special theory of relativity. The last and the most famous aspect of the special theory of relativity is the revelation that mass is a form of energy and that energy has mass. In Einstein's words, energy has mass and mass represents energy. Although this sounds shocking in one sense, in the sense that we have believed ever so long that matter, stuff, is different from energy, just as the body is different from the mind, another form of the same theory. In another sense, it sounds surprisingly natural. The matter-energy dichotomy goes back at least as far as the Old Testament. Genesis portrays man as a sort of ceramic creation. God scoops up a handful of clay, matter, and breathes life, energy, into it. The Old Testament is a product of the Western world, or the other way around. Physics also is a product of the Western world. In the East, however, there never has been much philosophical or religious, only in the West are these two separate, confusion about matter and energy. The world of matter is a relative world and an illusory one. Illusory not in the sense that it does not exist, but illusory in the sense that we do not see it as it really is. The way it really is cannot be communicated verbally, but in the attempt to talk around it, Eastern literature speaks repeatedly of dancing energy and transient, impermanent forms. This is strikingly similar to the picture of physical reality emerging from high-energy particle physics. Buddhist literature does not speak of learning new things about reality, but about removing veils of ignorance that stand between us and what we already are. Perhaps this accounts for the fact that the preposterous claim that mass is only a form of energy is unexpectedly palatable. The formula which expresses the relationship of mass to energy is the most famous formula in the world. E equals mc squared. The energy contained in a piece of matter is equal to the mass of the matter multiplied by an extraordinary large number. The speed of light squared. This means that even the very tiniest particle of matter has within it a tremendous amount of concentrated energy. Although Einstein didn't know it at the time, he discovered the secret of stellar energy. Stars continuously convert matter into energy. It is because of the very large ratio of energy released to matter consumed that stars can continue to burn through countless millennia. At the center of a star, hydrogen atoms, the primordial stuff of the physical world, are squeezed together so tightly by the enormous gravitational force of the star's dense mass that they fuse together, making a new element, helium. Every 4 hydrogen atoms become 1 helium atom. However, the mass of 1 helium atom is not the same as the mass of 4 hydrogen atoms. It is slightly less. This small difference in mass is released as radiant energy, heat and light. The process of fusing lighter elements into heavier elements is called, of course, fusion. The fusion of hydrogen into helium causes a hydrogen explosion. In other words, a young burning star literally is one huge, continuously exploding hydrogen bomb. The formula E equals mc squared also resulted in the atomic bomb. Atomic bombs and atomic reactors obtain energy from mass by the process of fission, which is the opposite of fusion. Instead of fusing smaller atoms into larger ones, the process of fission splits atoms of uranium, which are quite large, into atoms which are smaller. And this is done by firing a subatomic particle, a neutron, at an atom of uranium. When the neutron hits the uranium atom, it splits into lighter atoms, but the mass of these smaller atoms together is less than the mass of the parent atom of uranium. The difference in mass explodes into energy. This process also produces additional neutrons which fly off to strike other uranium atoms, creating more fissions, more light atoms, more energy, and more neutrons. The whole phenomenon is called a chain reaction. An atomic bomb is an uncontrolled chain reaction. A hydrogen fusion bomb is produced by detonating an atomic fission bomb in the midst of hydrogen. The heat from the atomic explosion, in place of the heat of friction caused by gravity, fuses hydrogen atoms into helium atoms and releases heat in the process, which fuses together more hydrogen atoms, releasing more heat, and so on. There is no limit to the size of a potential hydrogen bomb, and it is constructed from the most plentiful element in the universe. For better or worse, a major revelation of the special theory of relativity is that mass and energy are different forms of the same thing. Like space and time, they are not separate entities. There is no qualitative difference between mass and energy. There is only mass energy. Mathematically, this discovery meant that the 2 conservation laws of mass and energy could be replaced by a single conservation law of mass energy. A conservation law is a simple statement that a quantity of something, whatever it may be, never changes no matter what happens. For example, suppose that there were a conservation law governing the number of guests at a party. If such a thing were true, we would notice that every time a new guest arrived at the party, some other guest would leave. Similarly, every time a guest at the party left, another one would arrive. The rate of guest turnover at the party might be great or small, and the guests might arrive and depart singly or in groups. But in all circumstances, the number of guests at the party would remain the same. The conservation law concerning energy says that the total amount of energy in the universe always has been, and always will be, the same. We can convert energy from one form to another, like mechanical energy to thermal energy via friction. But the total amount of energy in the universe does not change. Similarly, the law of conservation of matter says that the total amount of matter in the universe always has been and always will be the same. We can convert matter from one form to another, like ice to water or water to steam, but the total amount of matter in the universe does not change. General nonsense. The general theory of relativity shows us that our minds follow different rules than the real world does. A rational mind, based on the impressions that it receives from its limited perspective, forms structures which thereafter determine what it further will and will not accept freely. From that point on, regardless of how the real world actually operates, this rational mind, following its self-imposed rules, tries to superimpose on the real world its own version of what must be. This continues until at long last a beginner's mind cries out, "This is not right. What must be is not happening. I have tried and tried to discover why this is so. I have stretched my imagination to the limit to preserve my belief in what must be. The breaking point has come. Now I have no choice but to admit that the must I have believed in does not come from the real world, but from my own head." This narrative is not poetic hyperbole. It is a concise description of the major conclusion of the general theory of relativity and the means by which it was reached. The limited perspective is the perspective of our three-dimensional rationality and its view of one small part of the universe, the part into which we were born. The things that must be are the ideas of geometry, the rules governing straight lines, circles, triangles, etc. The beginner's mind was Albert Einstein's. The long-held belief was that these rules govern, without exception, the entirety of the universe. What Einstein's beginner's mind realized was that this is so only in our minds. Einstein discovered that certain laws of geometry are valid only in limited regions of space. This makes them useful since our experience physically is limited to very small regions of space, like our solar system. However, as our experience expands, we encounter more and more difficulty in trying to superimpose these rules upon the entire expanse of the universe. Einstein was the first person to see that the geometrical rules, which apply to one small part of the universe, as seen from a limited perspective like ours, are not universal. This freed him to behold the universe in a way that no person had seen it before. What he saw is the content of the general theory of relativity. Einstein did not set out to prove anything about the nature of our minds. His interest was in physics. "Our new idea," he wrote, "is simple: to build a physics valid for all coordinate systems." The fact that he did illustrate something of importance about the way that we structure our perceptions is indicative of an inevitable trend toward the merger of physics and psychology. How did Einstein get from a theory of physics to a revolutionary statement of geometry? How did that lead to a significant insight into our mental processes? The answer to these questions is one of the least known, but one of the most important and intriguing intellectual adventures recorded. Einstein started with his special theory of relativity. As successful as it was, Einstein was not satisfied with it because it applied only to coordinate systems moving uniformly relative to each other. Is it possible, thought Einstein, to explain the same phenomenon as seen from two different frames of reference, one of them moving uniformly and the other of them moving non-uniformly, in such a way that there is a consistent explanation for the phenomenon in terms of both the uniformly moving frame of reference and the non-uniformly moving frame of reference? In other words, can we describe events which happen in a coordinate system which is moving non-uniformly in terms which are meaningful to an observer in a coordinate system which is moving uniformly and the other way around? Can we create one physics that is valid for observers in both frames of reference? Yes, discovered Einstein, it is possible for observers in the two different frames of reference to relate in a manner which is both meaningful in terms of their own state of motion and in terms of the other's state of motion. To illustrate this, he used another famous thought experiment. Imagine an elevator in an extraordinarily tall building. The cable which supports the elevator has snapped, and the elevator is plummeting downward. Inside the elevator are several physicists. They're not aware that the cable has broken, and since there are no windows, they cannot look outside. The question is, what is the appraisal of this situation by the observers on the outside of the elevator, us, and by the observers on the inside of the elevator, the physicists. Since this is an idealized experiment, we can disregard the effects of friction and the resistance of the air. To us, the situation is apparent. The elevator is falling, and soon it will strike the earth, and all of its inhabitants will be dead. As the elevator falls, it accelerates according to Newton's law of gravity. The motion of the elevator is not uniform, but accelerated, because of the gravitational field of the earth. We can predict many things that might happen inside the elevator. For example, if someone inside the elevator dropped a handkerchief, nothing would happen. It would appear to the inside observers to float where it was released, because it would be accelerating toward the earth at the same rate as the elevator and the people inside of it. Nothing really would be floating. Everything would be falling. But since everything would be falling at the same rate, there would be no change in their relative positions. To a generation of physicists born and brought up inside the elevator, however, things would appear quite differently. To them, dropped objects do not fall. They simply hang in mid-air. If someone gives a floating object a shove, off it goes in a straight line until it hits the side of the elevator. To the observers inside the elevator, there are no forces acting on any objects inside the elevator. In short, the observers inside the elevator would conclude that they are in an inertial coordinate system. The laws of mechanics are perfectly valid. Their experiments always produce results which agree exactly with theoretical predictions. An object at rest remains at rest. An object in motion remains in motion. Moving objects are deflected from their paths only by forces which are proportional to the amount of deflection. For every reaction, there is an equal and opposite reaction. If we give a shove to a floating chair, it goes off in one direction, and we go off in the opposite direction with an equal momentum, although with a slower speed because of our greater mass. The inside observers have a consistent explanation for the phenomena inside the elevator. They are in an inertial coordinate system, and they can prove it by the laws of mechanics. The outside observers also have a consistent explanation for the phenomena inside the elevator. The elevator is falling in a gravitational field. Its passengers are unaware of this because without being able to see outside the elevator, there is no way for them to detect it while they are falling. Their coordinate system is an accelerated motion, even though they believe that it is not moving at all. The bridge between these two explanations is gravity. The falling elevator is a pocket edition of an inertial coordinate system. A real inertial coordinate system is not limited in space or time. The elevator edition is limited in both. It is limited in space because a moving object inside the elevator will not move in a straight line forever, but only until it reaches one of the walls of the elevator. It is limited in time because sooner or later the elevator and its passengers are going to collide with the earth, ending their existence abruptly. In short, both in the need to cast off ordinary thought processes, and ultimately to go beyond thought altogether, and in the perception of reality as one unity, the phenomenon of enlightenment and the science of physics have much in common. Enlightenment is a state of being. Like all states of being, it is indescribable. It is a common misconception, literally, to mistake the description of a state of being for the state itself. For example, try to describe happiness. It is impossible. We can talk around it. We can describe the perspectives and actions that usually accompany a state of happiness, but we cannot describe happiness itself. Happiness and the description of happiness are two different things. Happiness is a state of being. That means that it exists in the realm of direct experience. It is the intimate perception of emotions and sensations which, indescribable in themselves, constitute the state of happiness. The word happiness is the label or symbol which we pin on this indescribable state. Happiness belongs to the realm of abstractions or concepts. A state of being is an experience. A description of a state of being is a symbol. Symbols and experience do not follow the same rules. This discovery that symbols and experience do not follow the same rules has come to the science of physics under the formidable title of quantum logic. The possibility that separate parts of reality, like you and I and tugboats, may be connected in ways which both our common experience and the laws of physics belie, has found its way into physics under the name of Bell's theorem. Bell's theorem and quantum logic take us to the farthest edges of the theoretical physics. Many physicists have not even heard of them. Bell's theorem and quantum logic, currently, are unrelated. Proponents of one seldom are interested in the other. Nonetheless, they have much in common. They are what is really new in physics. Of course, laser fusion, fusing atoms with high-energy light beams, and the search for quarks generally are considered to be the frontiers of theoretical physics. In a certain sense they are. However, there is a big difference between these projects and Bell's theorem and quantum logic. Laser fusion research and the great quark hunt are endeavors within the existing paradigms of physics. A paradigm is an established thought process, a framework. Both quantum logic and Bell's theorem are potentially explosive in terms of existing frameworks. The first, quantum logic, calls us back from the realm of symbols to the realm of experience. The second, Bell's theorem, tells us that there is no such thing as separate parts. All of the parts of the universe are connected in an intimate and immediate way, previously claimed only by mystics and other scientifically objectionable people. The central mathematical element in quantum theory, the hero of the story, is the wave function. The wave function is that mathematical entity which allows us to determine the possible results of an interaction between an observed system and an observing system. The celebrated position held by the wave function is due not only to Erwin Schrödinger, who discovered it, but also to the Hungarian mathematician John von Neumann. In 1932, von Neumann published a famous mathematical analysis of quantum theory called The Mathematical Foundations of Quantum Mechanics. In this book, von Neumann, in effect, asked the question, if a wave function, this purely abstract mathematical creation, actually should describe something in the real world, what would that something be like? The answer that he deduced is exactly the description of a wave function that we already have discussed. This strange animal constantly would change with the passage of time. Each moment it would be different than the moment before. It would not be a simple mixture of possibilities. It would be a sort of organic whole whose parts are changing constantly, but which nonetheless is somehow a thing in itself. This thing in itself would continue to develop indefinitely until an observation, measurement, is made on the observed system which it represents. If the observed system is a photon propagating in isolation, the wave function representing this photon would contain all of the possible results of the photon's interaction with the measuring device, like a photographic plate. For example, the possibilities contained in the wave function might be that the photon will be detected in area A of the photographic plate, that the photon will be detected in area B of the photographic plate, and that the photon will be detected in area C of the photographic plate. Once the photon is set in motion, the wave function associated with it would continue to develop or change according to a causal law, the Schrödinger wave equation, until the photon interacts with the observing system. At that instant, one of the possibilities contained in the wave function would actualize, and the other possibilities contained in the wave function would cease to exist. They simply would disappear. The wave function, that strange animal that von Neumann was attempting to describe, would collapse. The collapse of this particular wave function would mean that the probability of one of the possible results of the photon measuring device interaction became 1. It happened. And the probability of the other possibilities became 0. They were no longer possible. After all, a photon can be detected only in one place at a time. The wave function, according to this view, is not quite a thing, yet it is more than an idea. It occupies that strange middle ground between idea and reality, where all things are possible, but none are actual. Heisenberg likened it to Aristotle's potential, and this approach has unconsciously shaped the language and therefore the thinking of most physicists, even those who consider the wave function to be a mathematical fiction, an abstract creation whose manipulation somehow yields the probabilities of real events which happen in real versus mathematical space and time. Needless to say, this approach also has caused a great deal of confusion, which is as unclear today as it was in von Neumann's time. For example, exactly when does the wave function collapse? The problem of measurement. Is it when the photon strikes the photographic plate? Is it when the photographic plate is developed? Is it when we look at the developed plate? Exactly what is it that collapses? Where does the wave function live before it collapses? And so on. This view of the wave function, that it can be described as a real thing, is generally the view of the wave function attributed to von Neumann. However, the real wave function description is only one of the two approaches to understanding quantum phenomena, which he discussed in the mathematical foundations of quantum mechanics. The second approach, to which von Neumann devoted much less time, is a re-examination of the language by which it is necessary to express quantum phenomena. In the section Projections as Propositions, he wrote, "The relation between the properties of a physical system, on the one hand, and the projection's wave function on the other, makes possible a sort of logical calculus with these. However, in contrast to the concepts of ordinary logic, this system is extended by the concepts of simultaneous decidability, the uncertainty principle, which is characteristic for quantum mechanics. This suggestion that the novel properties of quantum theory can be used to construct a logical calculus, which is in contrast to the concepts of ordinary logic, is what von Neumann considered the alternative to describing wave functions as real things. Most physicists, however, have adopted a third explanation of wave functions. They dismiss them as purely mathematical constructions, abstract fictions which represent nothing in the world of reality. And unfortunately, this explanation leaves forever unanswered the question, how, then, can wave functions predict so accurately probabilities which can be verified through actual experience? In fact, how can wave functions predict anything when they are defined as completely unrelated to physical reality? This is a scientific version of the philosophical question, how can mind influence matter? Von Neumann's second approach to understanding the paradoxical puzzles of quantum phenomena took him far beyond the boundaries of physics. This brief work pointed to a fusion of ontology, epistemology, and psychology, which only now is beginning to emerge. In short, the problem, said von Neumann, is in the language. Herein lies the germ of what was to become quantum logic. In pointing to the problem of language, von Neumann put his finger on why it is so difficult to answer the question, what is quantum mechanics? Mechanics is the study of motion. Therefore, quantum mechanics is the study of the motion of quanta. But what are quanta? According to the dictionary, a quantum is a quantity of something. The question is, a quantity of what? A quantum is a piece of action, a piece of the action. The problem is that a quantum can be like a wave, and then again it can be like a particle, which is everything that a wave isn't. And furthermore, when a quantum is like a particle, it is not like a particle in the ordinary sense of the word. A subatomic particle is not a thing. We cannot determine simultaneously its position and momentum. A subatomic particle, a quantum, is a set of relationships or an intermediate state. It can be broken up, but out of the breaking come more particles as elementary as the original. Those who are not shocked when they first come across quantum theory, said Niels Bohr, cannot possibly have understood it. Quantum theory is not difficult to explain because it is complicated. Quantum theory is difficult to explain because the words which we must use to communicate it are not adequate for explaining quantum phenomena. This was well known and much discussed by the founders of quantum theory. Max Born, for example, wrote, "The ultimate origin of the difficulty lies in the fact, or philosophical principle, that we are compelled to use words of common language when we wish to describe a phenomenon, not by logical or mathematical analysis, but by a picture appealing to the imagination. Common language is grown by everyday experience and can never surpass these limits. Classical physics has restricted itself to the use of concepts of this kind. By analyzing visible motions, it has developed two ways of representing them by elementary processes: moving particles and waves. There is no other way of giving a pictorial description of motions. We have to apply it even in the region of atomic process, where classical physics break down." The difference between experience and symbol is the difference between mythos and logos. Logos imitates, but can never replace experience. It is a substitute for experience. Logos is the artificial construction of dead symbols which mimics experience on a one-to-one basis. Classical physical theory is an example of a one-to-one correspondence between theory and reality. Einstein argued that no physical theory is complete unless every element in the real world has a definite counterpart in the theory. Einstein's theory of relativity is the last great classical theory, even though it is a part of the new physics, because it is structured in a one-to-one way with phenomena. Unless a physical theory has one-to-one correspondence with phenomena, argued Einstein, it is not complete. Whatever the meaning assigned to the term complete, the following requirement for a complete theory seems to be a necessary one. Every element of the physical reality must have a counterpart in the physical theory. Quantum theory does not have this one-to-one correspondence between theory and reality. It cannot predict individual events, only probabilities. According to quantum theory, individual events are chance happenings. There are no theoretical elements in quantum theory to correspond with each individual event that actually happens. Therefore, quantum theory, according to Einstein, is incomplete. And this was a basic issue of the famous Bohr-Einstein debates. Mythos points toward experience, but it does not replace experience. Mythos is the opposite of intellectualism. Ceremonial chants at primitive rituals, like football games, are good examples of mythos. They endow experience with value, originality, and vitality, but they do not seek to replace it. Theologically speaking, logos is the original sin, the eating of the fruit of knowledge, the expulsion from the Garden of Eden. Historically speaking, logos is the growth of the literary revolution, the birth of the written tradition out of the oral tradition. From any point of view, logos literally is a dead letter. Knowledge, wrote E. E. Cummings, is a polite word for dead, but not buried imagination. He was talking about logos. Our problem, according to Finkelstein, is that we cannot understand subatomic phenomena or any other kind of experience through the use of symbols alone, as Heisenberg observed. The concepts initially formed by abstraction from particular situations or experiential complexes acquire a life of their own. Getting lost in the interaction of symbols is analogous to mistaking the shadows on the wall of the cave for the real world outside the cave, which is direct experience. The answer to this predicament is to approach subatomic phenomena, as well as experience in general, with a language of mythos, rather than a language of logos. Finkelstein put it this way: if you want to envision a quantum as a dot, then you are trapped. You are modeling it with classical logic. The whole point is that there is no classical representation for it. We have to learn to live with the experience. Question: how do you communicate the experience? Answer: you don't. But by telling how you make quanta and how you measure them, you enable others to have it. According to Finkelstein, a language of mythos, a language which alludes to experience, but does not attempt to replace it or to mold our perception of it, is the true language of physics. This is because not only the language that we use to communicate our daily experience, but also mathematics, follows a certain set of rules, classical logic. Experience itself is not bound by these rules. Experience follows a much more permissive set of rules, quantum logic. Quantum logic is not only more exciting than classical logic, it is more real. It is based not upon the way that we think of things, but upon the way that we experience them. When we try to describe experience with classical logic, which is what we've been doing since we learned to write, we put on a set of blinders, so to speak, which not only restricts our field of vision, but also distorts it. These blinders are the set of rules known as classical logic. The rules of classical logic are well defined. They are simple. The only problem is that they do not correspond to experience. The most important difference between the rules of classical logic and the rules of quantum logic involves the law of distributivity. The law of distributivity, or the distributive law, says that A and B, or C, is the same as A and B, or A and C. In other words, I flip a coin and it comes up heads or tails has the same meaning as I flip a coin and it comes up heads, or I flip a coin and it comes up tails. The distributive law, which is a foundation of classical logic, does not apply to quantum logic. This is one of the most important but least understood aspects of von Neumann's work. In 1936, von Neumann and his colleague Gerrit Birkhoff published a paper which laid the foundations of quantum logic. In it they used an example of a familiar to physicists phenomenon to disprove the distributive law. By so, they demonstrated mathematically that it's impossible to describe experience, including subatomic phenomena, with classical logic, because the real world follows different rules. The rules that experience follows, they called quantum logic. The rules which symbols follow, they called classical logic. Finkelstein uses a version of Birkhoff and von Neumann's example to disprove the law of distributivity. Finkelstein's demonstration requires only 3 pieces of plastic. Polarizers are a special kind of light filter, and most frequently they are made of stretched sheets of plastic material in which all the molecules are elongated and aligned in the same direction. These long, slender molecules are responsible for the polarization of the light, which passes through them. The polarization of light can be understood most easily as a wave phenomenon. Light waves from an ordinary light source, like the sun, emanate in every fashion vertically, horizontally, and every way in between. This does not mean only that light radiates from a source in all directions. It means that in any given beam of light, some of the light waves are vertical, some of the light waves are horizontal, some are diagonal, and so forth. To a light wave, a polarizer looks something like a picket fence. Whether it can get through the fence or not depends upon whether it is aligned with the fence or not. If the polarizer is aligned vertically, only the vertical light waves make it through. All of the other light waves are obstructed. All of the light waves that pass through a vertical polarizer are aligned vertically, and this light is called vertically polarized light. If the polarizer is aligned horizontally, only the horizontal light waves make it through. All of the other light waves are obstructed. All of the light waves that pass through a horizontal polarizer are aligned horizontally. This light is called horizontally polarized light. No matter how the polarizer is aligned, all of the light waves passing through it are aligned in the same plane. The arrows on the polarizers indicate the direction in which the light passing through them is polarized, which way the molecules in the plastic are elongated. According to quantum mechanics, diagonally polarized light is not a mixture of horizontally polarized light and vertically polarized light. We cannot simply say that the horizontal components of the diagonally polarized light pass through the horizontal polarizer and the vertical components of the diagonally polarized light pass through the vertical polarizer. According to quantum mechanics, diagonally polarized light is a separate thing in itself. How can a separate thing in itself get through all 3 filters, but not through 2 of them? If we consider light as a particle phenomenon, this paradox becomes graphic. Namely, how can one photon be broken down into a horizontally polarized component and a vertically polarized component? By definition, it can't. This paradox is at the heart of the difference between quantum logic and classical logic. It is caused by our thought processes, which are following the rules of classical logic. Our intellect tells us that what we are seeing is impossible. After all, a single photon must be polarized one way or the other. But nonetheless, whenever we insert a diagonal polarizer between a horizontal polarizer and a vertical polarizer, we see light where there was none before. Our eyes are ignorant of the fact that what they are seeing is impossible, and that is because experience does not follow the rules of classical logic. It follows the rules of quantum logic. The thing in itself of diagonally polarized light reflects the true nature of experience. Our symbolic thought process imposes upon us the categories of either or. It confronts us always with either this or that, or a mixture of this and that. It says that polarized light is either vertically polarized or horizontally polarized, or a mixture of vertically and horizontally polarized light. Thus are the rules of classical logic, the rules of symbols. In the realm of experience, nothing is either this or that. There's always at least one more alternative, and often an unlimited number of them. Finkelstein put it this way in reference to quantum theory: there are no waves in the game. The equation that the game obeys is a wave equation. But there are no waves running around. This is one of the mountains of quantum mechanics. There are no particles running around either. What's running around are quanta, the third alternative. To be less abstract, imagine that we have two different pieces from a chess set, say a bishop and a pawn. If these macroscopic chess pieces followed the same rules as quantum phenomena, we would not be able to say that there is nothing between being either a bishop or a pawn. Between the extremes of bishop and pawn is a creature called a bichon. A bichon is neither a bishop nor a pawn, nor is it half a bishop and half a pawn glued together. A bichon is a separate thing in itself. It cannot be separated into its pawn component and its bishop component any more than a puppy, which is half collie and half German shepherd, can be separated into its collie component and its German shepherd component. There is more than one type of bichon between the extremes of bishop and pawn. The bichon that we have been describing is 1/2 part bishop and 1/2 part pawn. Another type of bichon is 1/3 part bishop and 2/3 part pawn. Still another type of bichon is 3/4 part bishop and 1/4 part pawn. In fact, for every possible proportion of parts bishop to parts pawn, there exists a bichon, which is quite distinct from all the others. A bichon is what physicists call a coherent superposition. A superposition is one thing or more imposed on another. A double exposure, the bane of careless photographers, is a superposition of one photograph on another. A coherent superposition, however, is not simply the superposition of one thing on another. A coherent superposition is a thing in itself which is as distinct from its components as its components are from each other. Diagonally polarized light is a coherent superposition of horizontally polarized light and vertically polarized light. Quantum physics abounds with coherent superpositions. In fact, coherent superpositions are at the heart of the mathematics of quantum mechanics. Wave functions are coherent superpositions. Every quantum mechanical experiment has an observed system. Every observed system has an associated wave function. And the wave function of a particular observed system, like a photon, is the coherent superposition of all the possible results of an interaction between the observed system and a measuring system, like a photographic plate. The development in time of this coherent superposition of possibilities is described by Schrödinger's wave equation. And using this equation, we can calculate the form of this thing in itself, this coherent superposition of possibilities, which we call a wave function, for any given time. Having done that, we then can calculate the probability of each possibility contained in the wave function at that particular time. This gives us a probability function, which is not the same as a wave function, but is calculated from a wave function. In a nutshell, that is the mathematics of quantum physics. How do coherent superpositions reflect experience? Pure experience is never restricted to merely two possibilities. Our conceptualization of a given situation may create the illusion that each dilemma has only two horns. But this illusion is caused by assuming that experience is bound by the same rules as symbols. In the world of symbols, everything is either this or that. In the world of experience, there are more alternatives available. For example, consider the judge who must try his own son in a court of law. The law allows only two verdicts. He's guilty and he is innocent. For the judge, however, there's another possible verdict, namely, he is my son. The fact that we prohibit judges from trying cases in which they have a personal interest is a tacit admission that experience is not limited to the categorical alternatives of guilty and innocent, or good and bad, etc. Only in the realm of symbols is the choice so clear. During the Lebanese Civil War, a story goes, a visiting American was stopped by a group of masked gunmen. One wrong word could cost him his life. "Are you Christian or Muslim?" they asked. "I am a tourist," he cried. The way that we pose our questions often illusory limits our responses. In this case, the visitor's fear for his life broke through this illusion. Similarly, the way that we think our thoughts illusory limits us to a perspective of either or. Experience itself is never so limited. There is always an alternative between every this and every that. The recognition of this quality of experience is an integral part of quantum logic. And physicists engage in a particular kind of dance which is foreign to most of us. Being around them for any length of time is like entering another culture. Within this culture, every statement is subject to the challenge, prove it. When we tell a friend, "I feel great this morning," we do not expect him to say, "Prove it." However, when a physicist says experience is not bound by the same rules as symbols, he invites a chorus of prove-its. Until he can do this, he must preface his remarks with, "It is my opinion that..." Physicists are not very impressed with opinions. Unfortunately, this sometimes makes them narrow-minded to an extraordinary degree. If you are not willing to follow their dance, they won't dance with you. Their dance requires a proof for every assertion. A proof does not verify that an assertion is true, that this is the way the world really is. A scientific proof is a mathematical demonstration that the assertion in question is logically consistent. In the realm of pure mathematics, an assertion may have no relevance to the experience at all. Nonetheless, if it is accompanied by a self-consistent proof, it is accepted. If it is not, it is rejected. The same is true of physics, except that the science of physics imposes the additional requirement that the assertion relate to physical reality. So much for the relationship between the truth of a scientific assertion and the nature of reality. There isn't any. Scientific truth has nothing to do with the way that reality really is. A scientific theory is true if it is self-consistent and correctly correlates experience, predicts events. In short, when a scientist says that a theory is true, he means that it correctly correlates experience, and therefore it is useful. If we substitute the word useful whenever we encounter the word true, physics appears in its proper perspective. Birkhoff and von Neumann created a proof that experience violates the rules of classical logic. This proof, of course, is embedded in experience. In particular, it is based upon what does and does not happen, with various combinations of polarized light. Finkelstein uses a slightly modified version of Birkhoff and von Neumann's original proof to demonstrate quantum logic. The first step of this proof is to experiment with all of the possible combinations of horizontally, vertically, and diagonally polarized light. In other words, the first step is to do what we've done already: discover which light emissions pass through which polarizers. Observe for yourself that light passes through two vertical polarizers, two horizontal polarizers, two diagonal polarizers, a diagonal and a horizontal polarizer, and a diagonal and a vertical polarizer. All of these combinations are called allowed transitions because they actually happen. Similarly, observe for yourself that light does not pass through a horizontal and a vertical polarizer, or any other combination of polarizers oriented at right angles to each other. These combinations are called forbidden transitions because they never happen. The second step of the proof is to make a table of this information called a transition table. The row of letters on the left are emissions. An emission is just what it sounds like. In this case, an emission is a light wave that is emitted from a light bulb. The quotation parentheses quotation sign to the right of a letter indicates an emission. For example, quotation capital H parentheses quotation means horizontally polarized light emitting from a horizontal polarizer. The row of letters on the top are admissions. An admission is the reception of an emission. The quotation parentheses quote sign to the left of a letter indicates an admission. For example, H means a horizontally polarized light wave reaching an eyeball. Von Neumann's discovery that our thought processes, the realm of symbols, project illusory restrictions onto the real world is essentially the same discovery that led Einstein to the general theory of relativity. Einstein disproved the universality of Euclidean geometry. Until the general theory of relativity, Euclidean geometry had been accepted without question as the underlying structure of the universe. Birkhoff and von Neumann disproved the universality of classical logic. Until now, classical logic has been accepted without question as a natural reflection of the nature of reality. A powerful awareness lies dormant in these discoveries, an awareness of the hitherto unsuspected powers of the mind to mold reality, rather than the other way around. In this sense, the philosophy of physics is becoming indistinguishable from the philosophy of Buddhism, which is the philosophy of enlightenment. The end of science. A vital aspect of the enlightened state is the experience of an all-pervading unity. This and that no longer are separate entities. They are different forms of the same thing. Everything is a manifestation. It is not possible to answer the question, manifestation of what? Because the what is that which is beyond words, beyond concept, beyond form, beyond even space and time. Everything is a manifestation of that which is. That which is, is. Beyond these words lies the experience of that which is. The forms through which that which is manifests itself are each and every one of them perfect. We are manifestations of that which is. Everything is a manifestation of that which is. Everything and everybody is exactly and perfectly what it is. A 14th century Tibetan Buddhist, Longchenpa, wrote, "Since everything is but an apparition, perfect in being what it is, having nothing to do with good or bad, acceptance or rejection, one may well burst out in laughter." We might say God's in his heaven and all's well with the world, except that according to the enlightened view, the world couldn't be any other way. It is neither well nor not well. It simply is what it is. What it is perfectly what it is. It couldn't be anything else. It is perfect. I am perfect. I am exactly and perfectly who I am. You are perfect. You are exactly and perfectly who you are. If you are a happy person, then that is what you perfectly are, a happy person. If you are an unhappy person, then that is what you perfect are, an unhappy person. If you are a person who is changing, then that is what you perfectly are, a person who is changing. That which is that which is. That which is not is that which is. There is nothing which is not that which is. There is nothing other than that which is. Everything is that which is. We are a part of that which is. In fact, we are that which is. If we substitute subatomic particles for people in this scheme, we have a good approximation of the conceptual dynamics of particle physics. Yet there's another sense of which this aspect of unity has entered physics. The pioneers of quantum physics noticed a strange connectedness among quantum phenomena. Until recently, this oddity lacked any theoretical significance. It was regarded as an accidental feature which would be explained as the theory developed. A first possibility is that free will is an illusion. Contrafactualness fails. Perhaps there's no such thing as what would have happened if. Perhaps there can be only what is. In this case, we are led to a superdeterminism. And this is a determinism far beyond ordinary determinism. Only determinism states that once the initial situation of a system is established, the future of the system also is established, since it must develop according to inexorable laws of cause and effect. And this type of determinism was the basis of the great machine view of the universe. According to this view, however, if the initial situation of a system, like the universe, is changed, then the future of the system also is changed. According to superdeterminism, not even the initial situation of the universe could be changed. Not only is it impossible for things to be other than they are, it is even impossible that the initial situation of the universe could have been other than what it was. No matter what we are doing at any given moment, it is the only thing that ever was possible for us to be doing at that moment. Contrafactual definiteness also fails if the definiteness assumption in it fails. In this case, we do have a choice in the way that we perform our experiments, but what would have happened if does not produce any definite results? This alternative is just as strange as it sounds. It is also just what comes out of the many worlds interpretation of quantum mechanics. According to the many worlds theory, whenever a choice is made in the universe between one possible event and another, the universe splits into different branches. The function of Eastern religions, psychologies, is to allow the mind to escape the confines of the symbolic. According to this view, everything is a symbol, not only words and concepts, but also people and things. Beyond the confines of the symbolic lies that which is, pure awareness, the experience of the suchness of reality. Nonetheless, every Eastern religion resorts to the use of symbols to escape the realm of the symbolic. Some disciplines use symbols more than others, but all of them use symbols in one form or another. Therefore, the question arises, if pure awareness is considered distinct from the content of awareness, in what ways specifically does the content of awareness affect the realization of pure awareness? What types of content prompt the mind to leap forward? What enables it to activate the self-fulfilling capability to transcend itself? It is very difficult to answer this question. Any answer is only a point of view. A point of view itself is limiting. To understand something is to give up some other way of conceiving it. This is another way of saying that the mind deals in forms of limitation. Nonetheless, there is a relationship between the content of awareness and the ability of the mind to transcend itself. Reality is what we take to be true. What we take to be true is what we believe. What we believe is based upon our perceptions. What we perceive depends upon what we look for. What we look for depends upon what we think. What we think depends upon what we perceive. What we perceive determines what we believe. What we believe determines what we take to be true. What we take to be true is our reality. The central focus of this process, initially at any rate, is what we think. We at least can say that allegiance to a symbol of openness, Christ, Buddha, Krishna, the infinite diversity of nature, etc., seems to open the mind, and that an open mind is often the first step in the process of enlightenment. The psychological gestalt of physics has shifted radically in the last century to one of extreme openness. In the middle 1800s, Newtonian mechanics was at its zenith. There seemed to be no phenomenon which could not be explained in terms of mechanical models. All mechanical models were subject to long-established principles. The chairman of the physics department at Harvard discouraged graduate study because so few important matters remained unsolved. In a speech to the Royal Institution in 1900, Lord Kelvin reflected that there were only two clouds on the horizon of physics, the problem of black body radiation and the Michelson-Morley experiment. There was no doubt, said Kelvin, that they soon would be gone. He was wrong. Kelvin's two clouds signaled the end of the era that began with Galileo and Newton. The problem of black body radiation led to Planck's discovery of the quantum of action. Within 30 years, the entirety of Newtonian physics became a special limiting case of the newly developing quantum theory. The Michelson-Morley experiment foreshadowed Einstein's famous theories of relativity. By 1927, the foundations of the new physics, quantum mechanics, and relativity were in place. In contrast to Kelvin's time, the allegiance of physicists today is to a symbol of extreme openness. Isidor Rabi, Nobel Prize winner, wrote in 1975, "I don't think that physics will ever have an end. I think that the novelty of nature is such that its variety will be infinite, not just in changing forms, but in the profundity of insight and the newness of ideas." Stapp wrote in 1971, "Human inquiry can continue indefinitely to yield important new truths." The what we think of physicists today is that the physics of nature, like human experience itself, is infinitely diverse. Eastern religions have nothing to say about physics, but they have a great deal to say about human experience. In Hindu mythology, Kali, the Divine Mother, is the symbol for the infinite diversity of experience. Kali represents the entire physical plane. She is the drama, tragedy, humor, and sorrow of life. She's the brother, father, sister, mother, lover, and friend. She is the fiend, monster, beast, and brute. She's the sun and the ocean. She is the grass and the dew. She is our sense of accomplishment and our sense of doing worthwhile. Our thrill of discovery is a pendant on her bracelet. Our gratification is a spot of color on her cheek. Our sense of importance is the bell on her toe. This full and seductive, terrible and wonderful Earth Mother always has something to offer. Hindus know the impossibility of seducing her or conquering her and the futility of loving her or hating her, so they do the only thing they can do. They simply honor her. In a particular story, Kali, the Divine Mother, is Sita, the wife of God. Ram is God. Ram, Sita, and Lakshman, who is Ram's brother, are walking along a jungle trail. The path is so narrow that most of the time Lakshman can only see Sita, who walks between him and Ram. Every so often, however, the path turns in such a way that Lakshman can see his brother, God. These powerful metaphors have application to the developing drama of physics. Although most physicists have little patience, professionally, with metaphors, physics itself has become a powerful metaphor. 20th century physics is a story of a journey from intellectual entrenchment to intellectual openness. despite the conservative prove-it-to-me nature of individual physicists. The realization that the discoveries of physics never will end has brought physicists, as well as those who have followed the story of physics, to an extremely fertile plateau. This realization invites the intellect to leap forward. The Wu Li masters know that physicists are doing more than discovering the endless diversity of nature. They are dancing with Kali, the divine mother of Hindu mythology. Buddhism is both a philosophy and a practice. Buddhist philosophy is rich and profound. Buddhist practice is called Tantra. Tantra is a Sanskrit word meaning to weave. There is little that can be said about Tantra. It must be done. Buddhist philosophy reached its ultimate development in the 2nd century A.D. No one has been able to improve much on it since then. The distinction between Buddhist philosophy and Tantra is well defined. Buddhist philosophy can be intellectualized. Tantra cannot. Buddhist philosophy is a function of the rational mind. Tantra transcends rationality. The most profound thinkers of the Indian civilization discovered that words and concepts could take them only so far. Beyond that point came the actual doing of a practice, the experience of which was ineffable. This did not prevent them from progressively refining the practice into an extremely effective and sophisticated set of techniques, but it did prevent them from being able to describe the experiences which these techniques produce. The practice of Tantra does not mean the end of rational thought. It means the integration of thought based on symbols into larger spectrums of awareness. Enlightened people still remember their zip codes. The development of Buddhism in India shows that a profound and penetrating intellectual quest into the ultimate nature of reality can culminate in, or at least set the stage for, a quantum leap beyond rationality. In fact, on an individual level, this is one of the roads to enlightenment. Tibetan Buddhism calls it the path without form, or the practice of mind. The path without form is prescribed for people of intellectual temperament. The science of physics is following a similar path. The development of physics in the 20th century already has transformed the consciousness of those involved with it. The study of complementarity, the uncertainty principle, quantum field theory, and the Copenhagen interpretation of quantum mechanics produces insights into the nature of reality very similar to those produced by the study of Eastern philosophy. The profound physicists of this century increasingly have become aware that they are confronting the ineffable. Max Planck, the father of quantum mechanics, wrote, "Science means unresting endeavor and continually progressing development toward an aim which the poetic intuition may apprehend, but which the intellect can never fully grasp." We are approaching the end of science. The end of science does not mean the end of the unresting endeavor and continually progressing development of more and more comprehensive and useful physical theories. Enlightened physicists remember their zip codes, too. The end of science means the coming of Western civilization in its own time and in its own way into the higher dimensions of human experience. Professor G.F. Chu, chairman of the physics department at Berkeley, remarked in reference to a theory of particle physics, "Our current struggle with certain aspects of advanced physics may thus be only a foretaste of a completely new form of human intellectual endeavor, one that will not only lie outside physics, but will not even be describable as scientific. We need not make a pilgrimage to India or Tibet. There's much to learn there, but here at home, in the most inconceivable of places, amidst the particle accelerators and computers, our own path without form is emerging." Al Huang, the Tai Chi master who created the metaphor of Wu Li, once wrote, "Sooner or later, we reach a dead end when we talk." He could as well have said that sooner or later we go around in circles when we talk, since going around in a circle is one kind of dead end. As we sat in a cabin at Esselen and talked late into the night, my new friend David Finkelstein spoke to us softly. I think it would be misleading to call particles the entities involved in the most primitive events of the theory, quantum topology, because they don't move in space and time. They don't carry mass. They don't have charge. They don't have energy in the usual sense of the word. Question: so what is it that makes events at that level? Answer: who are the dancers and who the dance? They have no attributes other than the dance. Question: what is they? Answer: the things that dance, the dancers. My God, we're back to the title of the book.